Greenland, increasing the melt rate over the year. The speed up, the velocity of the ice in blue here, really increases dramatically at the beginning of the melt season and then tails off even as the runoff is increasing. And so really, this is a compare and contrast between in Antarctica, where we're thinking about how does the ocean affect the subglacial environment, versus in Greenland, where we're asking how does surface melting drain to the base and then affect the ice speed. And in both cases, we're interested in this muddy layer at the bottom here. This is mud and silt. And the behavior of that mud and silt depends intimately on the water pressure. And so the response of ice sheets to water at the base is that generically you add more water, it becomes more slippery at the base of the ice sheets and they flow faster. But there's some really interesting time-dependent dynamics in terms of how does that occur. So let's look at that in two different settings using two, as it were, physics experiments. We're going to look in Greenland at the drainage of superglacial lakes. This is like a Green's function point force applied to the Greenland ice sheet. Whereas in Antarctica, we're going to ask, how does the ocean affect the motion of the ice sheets by oscillating the water pressure using ocean tides? So here's a wonderful movie from Stevens et al., published in Nature 2015. They looked with a dense network of GPS receivers at the drainage of a superglacial lake that's about 10 square kilometers in size. They looked at, they looked here at, can I get that to play again? Yep. At the uplift of the ice and the increased motion of the ice due to the drainage of this lake. And what they find is that as time progresses, you get a transient signal just before the lake drains. As the lake drains, you rip open a huge fracture. All of that 10 square kilometers worth of lake drains in about an hour and a quarter, which must have been rather dramatic. And you see this uplift associated with that lake drainage event and a speed up of the ice associated with that. So the question I'm going to try and ask and answer today is, how does that water spread out at the base of the ice? And this is a kind of a nice reduced physics problem. You might recall from, for example, second year physics, that the deflection of an elastic beam depends on its bending stiffness. And so as that water drains to the base of the ice, you have to flex up this elastic sheet, which is the overlying ice. How does that work? Well, I'm going to skip the math very quickly here. We have pressure gradients, which can be elastic, which can be hydrostatic, that drives the water through a narrow gap, which is the opening gap underneath the ice. And that water flux spreads the water off to the far field, and that lubricates the base of the ice. And we'd like to understand exactly how does it spread? How does it get that far? There's an interesting problem here, which is related to a lot of other physics problems, nicely summarized here in a paper by Anne Jewell and Draga Filifizovic, Matthias Hale. Essentially, if you have an elastic sheet stuck down to the substrate, how do you get it off? Do you crack it off? Do you delaminate it off? Do you peel it off? There's all sorts of interesting physics that can play a role in how you get a piece of tape off the table. This is a classic problem studied by G.I. Taylor. Here in the ice sheet, it's a problem that Duncan Hewitt, Greg Cheney, and I have looked at. What we're really doing is peeling an elastic sheet off of a porous substrate. And the way that you get it off is you suck some of the fluid out of the porous substrate, and that allows this blister of water to spread out underneath the ice. So we put that into a mathematical model, and we can find this following type of behavior. This is for draining a superglacial lake. It inflates a blister that spreads out, is impacted by this subglacial till, this porous medium underneath. And then as that drainage event ceases, you slowly drain into the surrounding area. And the question is, does this bear any resemblance to the data? Well, here's a prediction of the height of that blister as a function of time from our model with spreading over a subglacial till. And that seems to do a reasonable job of understanding how far does that water get out underneath the subglacial environment in Greenland. Okay, so that's, as it were, the point force. Now let's look at a slightly different setting. This is the Rutford ice stream in Antarctica. And I'm really showing you now some observations from Brent Minshew at MIT, who uses satellite observations in SAR to measure the deflection of ice sheets. So on the top left here, you see the vertical deflection of the ice sheet over the tidal cycle. The ocean tides raise and lower the floating ice shelf. That's the part in red and blue here in this movie, and which is attached, of course, to the ice sheet, which is sitting on ground. Porous ground, I would argue, but ground nonetheless. So it's not going up and down. So we can see the tides wiggling the ice shelf up and down on tidal cycle. What's interesting is that Brent also measures the horizontal speed of the ice. And remember, this is the key thing that responds to the ocean warming in our initial slides of the climate. And we see that while the velocity of the ice is fast, we see a modulation which is tidally modulated. And the puzzle here is that it's tidally modulated on a 2-week or fortnightly variation, not the daily tidal variation. So how does that work? Well, this is another fluids problem, which you've probably studied when you stood with your feet at the beach watching the waves come in. Right, at the beach, when the waves come in and they're very thick and they come in fast, but as they drain out, the swash goes out slowly. Why is that? Well, it's similar to what happens in the subglacial hydrological setting. So we have the ice sheet, the shelf floating on the ocean, and as the ocean tide comes in, it fractures or peels this ice sheet off the bedrock. That's similar to the Greenland superglacial lake drainage problem. And so that's relatively rapid. On the way back, the outgoing tide is very slow, and it's slow because you have to use gravity to drain that water film, just like you do at the beach. And so that process of the tides going in and out responds non-linearly, and we can use, again, a fluid dynamic model where we conserve mass. We understand the fluid flux, again, driven by both hydrostatic and elastic pressure gradients, to understand the evolution of the grounding zone. This is something that a PhD student, Kasia Warburton, has done very elegantly recently. So here's a movie of that peeling process. As the tide comes in, the response of the ice is very fast, but as the ice sheet goes out, the response is very slow, and you leave behind a thick film of water underneath. Now, if you imagine asking this question about different grounding lines, where the grounding line slope is either large or small, the tidal amplitude is large or small, the permeability of the till is large or small, that means that you can filter the ocean tides in different ways, as shown on the right. So if the response both to the upgoing and downgoing tide is fast, you simply follow the ocean tides. And if it's slow, you stay at the high tide mark. And that helps us explain both the response of places like Beardmore Glacier and Rutford Glacier. Beardmore showing more of the daily tidal signal in the velocity, and Rutford showing more of this fortnightly variation. Okay, so that's superglacial lakes and Antarctic ice streams. And the key question here is, can we understand the natural forcing using our fluid dynamics of the subglacial processes? Now I'm going to do a rather schizophrenic switch and tell you where we can also use fluid dynamics to understand the climate, but now it's what might be our response to the climate perturbation, and how might we at least solve part of the problem, not anything like all of the problem, but what's a potential solution. So this is an idea that has been bandied around for quite a while, geological carbon storage. The idea is that you take CO2, which we would otherwise emit to the atmosphere, and you store it deep underground. And so to sort of dwell on that just a little bit further, the idea then is that you capture CO2 from stationary power plants, gas processing industry, and it's really hard to decarbonize areas of the industry where CO2 storage is now really thought to be potentially a big contributor. There's then a question about how do you transport it before you want to store it, and storage is typically deeply underground, where it will remain out of the atmospheric system for hundreds, if not thousands of years. So on the capture side, what's the process? The process is essentially to take the flue gas, the concentrated CO2, mix it with a solvent that then absorbs the CO2. You then need to apply some energy to get the CO2 back off of this solvent or solid absorbent. This is the same technology that would be used for direct air capture, for example, and it's an energy penalty, but I'd argue it's an energy penalty we might want to start paying in order to reduce the CO2 that we emit to the atmosphere. There's then a question about how do you transport it. The key two mechanisms that you might transport that CO2 are either pipelines or in shipping. Example of pipelines, already in the States, CO2 is shipped over essentially thousands of kilometers distance. In the moment, it's essentially extracted from volcanic sources and then used for enhanced oil recovery. And of course, for geological carbon storage, the idea would be to take the CO2 from anthropogenic industrial sources and store it not for enhanced oil recovery, but simply to get rid of the CO2. In the UK, we are fortunate in terms of our storage possibilities. There's a huge swath of the near offshore where there are lots of potential storage sites. There's even some infrastructure for getting that CO2 offshore in terms of existing pipelines. And so at least for the near next 50 to 100 years, we've got quite a significant storage potential in the near offshore UK environment. What are the physics challenges? Well, CO2, even at the depths that are being considered, and the depths are typically over 800 meters to a kilometer depth, is buoyant and it's less viscous, so it'll want to rise and spread. And in order to get it to stay down there, we need to trap it. And the ways that we might trap it are either structural, so underneath something impermeable, residual, so that's using capillary forces to keep the CO2 trapped in the rock, much like water stays in a sponge as you lift it out of the kitchen sink. And then solubility, if you dissolve CO2 in water, you get carbonated water. Carbonated water, it turns out, is heavier than uncarbonated water. So dissolving CO2 into water will result in heavy water that sinks and thereby stores more CO2. So those are the primary mechanisms. There's also mineral trapping, turning CO2 into rock, and that's typically only fast enough in particular geological settings, like in Iceland. CO2 storage has its own variant of the turbulence problem that we try and think of when modeling the atmosphere, and that's that rocks are complex. If you look at a cliff, you'll see this, that the sort of geological complexity goes anything from the millimeter to the kilometer scale. And so that's the key question: how do we understand CO2 flowing in heterogeneous rocks? But let me, as it were, just touch on one example of CO2 storage, which at least shows that it can be done, so long as there's the political will. And that, if anything, is the message I'd give for carbon storage. It's a technology that has been tried and has worked in the past, but it really relies, if it's going to be implemented, on societal and political will. So here's our type example. So what we have here is an image of the Sleipner project. The Sleipner project has been running since 1996, injecting about a megaton of CO2 per year underneath the North Sea, about halfway between Norway and Scotland. It's paid for by a $55 a ton tax on offshore CO2 emissions. Where do those CO2 emissions come from? There's a natural gas production facility called the Sleipner West Natural Gas Production Facility. They're extracting natural gas for sales to Europe. That natural gas, not uncommonly, has about 10% CO2 in the natural gas stream. So already they have to extract the CO2 at the offshore production facility. And that $55 a ton tax on CO2 emissions offshore that Norway instituted in the 90s is enough for the company to have been injecting that CO2 into the subsurface since 1996. They're injecting into what's called the Utsira sand formation. It's about a 200-meter thick sand body, like the beach sand, overlain by a thick mudstone. This is the Nordland Formation. That mudstone is relatively impermeable, so it's hard to get the CO2 through. So what happens is the CO2 rises from the point that it's injected and ponds underneath the mudstone. And there's no evidence so far that that CO2 has been migrating or leaking anywhere out of this particular formation. Why do I say that? Well, here's the evidence. Pleasantly enough, we have seismic surveys that map out the CO2 distribution every couple of years at the Sleipner site. Seismic survey is shipborne. There's essentially a acoustic bang that's set off, and we listen to echoes from beneath the sea surface on a long array of microphones. What we see is the following. So here's the seismic survey from pre-injection in 1994. You can see the boundary between the sand and the Nordland shale is this horizon here. In 2010, this is how that picture has changed. And what you see is a lot of bright reflections, which are the CO2 ponding underneath. The CO2 is essentially rising through this 200-meter thick sand, and it's hitting these thin layers of shale and spreading out underneath these thin layers of shale in about 9 different horizons. And those 9 horizons are demarcated or mapped here. So here's a picture, a cross-section of this rising plume of CO2. The injection point is schematically shown in red. And what we see is the progress of that plume from injection in 1996, and 94 is pre-injection, all the way through 2008, the mapping out of that plume as a function of time. And if we look straight down on that plume, you can see the plan form of the CO2 spreading at different horizons. Now, there's a lot of interesting physics in terms of how do we image it. That's the physics surrounding seismic imaging and processing of seismic imaging. I'm not going to talk in detail about that kind of imaging today. I want to talk about the fluid dynamics of how do we explain bizarre shapes like this guitar shapes feature up here at the very top of the plume. So the base of the plume here is at layer 1, the top is at layer 9. And that plume really expands and grows with time in the following snapshots from 1999 all the way through 2010 on the bottom right here. So how do we explain the rise and the flow of that CO2? Well, again, I'm going to rely on some fluid dynamical modeling. Here are 2 movies, courtesy of Chris McMinn from Oxford, showing the sort of behavior of the physics of the flow. So either the flow is driven by hydrostatic pressure gradients. So this is when you dribble honey on your toast and it spreads out on your toast because it's thick in the middle and it's thin on the edge. That's exactly what this animation is showing. The simulation of of the gradients and the thickness driving the spread. You can also have the flow up the slope, right? And so that's the along slope component of gravity driving the flow, just like if you tilt your toast and the honey starts sliding off your toast. So with those 2 pieces of physics, we can start to understand the motion of CO2. So on the left here, I've got an animation of our simulation using just this model of both its own thickness driven gravity current and also the upslope component. In the background to this, we have the seismically determined structure of the caprock. It's got a bowl at the top here, a little bit of a channel, a bowl here underneath where it's being injected. This looks like an old riverine channel on the seismics. And so the CO2 is essentially following that. And we can do a fairly good job of explaining where does the CO2 flow as a function of time if we can understand the properties of the rock that it's being injected into. So that gives you a sense of the kinds of fluid dynamics in terms of how does the CO2 flow. There are some other fluid dynamics that are important here. One is trapping. So I said there's trapping by surface tension. So on the top left is a reconstruction by Sally Benson at Stanford University of CO2 being driven into a rock core at reservoir temperatures and pressure, and then the pressure being relieved. And you can see that the surface tension is trapping globules of CO2 within the rock, just like water gets trapped in a sponge when you take it out of the kitchen sink. And on the right is the leading order, or the simplest reduced order model, which is that as this plume of CO2 sweeps through the reservoir, it leaves behind a fraction of its CO2 volume trapped within the rock by surface tension. So that's trapping by surface tension. The 2 movies on the bottom here are trapping by dissolution. So on the very bottom is the laboratory experiment that we've done in the lab in Cambridge. I'll just start it from the beginning again. What we've done is we've released a current of methanol and ethylene glycol into a glass beads filled with water in the interstices. The methanol ethylene glycol mix, or MEG, is less dense, so it's this blue mix, and so it spreads out over the water, but as it dissolves into the water, it produces something heavy. And that's like carbonated water being heavy compared to uncarbonated water. And so the volume of free-phase CO2, this dark blue stuff, reduces over time as it dissolves into the water, and that heavy water spreads out as a function of time. And so those are the two ways that we might think of trapping CO2, either through surface tension or through dissolution, both of which I'd argue are probably greatly enhanced by the natural heterogeneity within the rock. And that is a topic of quite some lively research at the moment in terms of how do we understand the impact of really heterogeneous rocks on dissolution processes and surface tension. Okay, so that is, as it were, a really whistle-stop tour of subglacial hydrology and also of CO2 storage. On CO2 storage, the real question is, can we store CO2 sufficiently at scale, ensuring that it's permanently trapped? Well, that's the sort of physics question. I think the answer to that is yes, and we've got almost 30 years now of injection history at Sleipner to say that yes, it's possible. There's a different question I could have put up here, which is, as a society, do we really want to do this? And that's a different question that, as a physicist, I'm not sure I'm quite so capable of answering, but I'll leave that one with you. Okay, thanks very much.
Amazing. Thank you so much, Professor. That was an excellent talk, very interesting. I will open the floor to any questions. You can pop those in the chat, or you can use the Google form, which Henry will monitor, and then he can read out any questions you guys have. I have a couple of questions. Firstly, would like to just ask about the glaciers you were talking about. You're talking about, I think it was Beardmore and Rutford. You said that one of them was modulated more daily and one was modulated with the fortnightly variation. Do you know why that is, or is it a topic of research?
Yeah, so let me find that slide. So here we are at Rutford and Beardmore. So the key variant here.
Oh, sorry, I don't think you're showing the screen.
Oh, sorry.
It's okay.
Thank you. Got it again?
Yeah.
Good. So the key distinguishing feature between Beardmore and Rutford is really the slope of the base. So you can imagine, let me just show you this picture of the beach again, because it's I think it's probably easier to imagine the beach case, right? When the slope of the beach is really gradual, the same height of wave will run up a huge distance and back, right? Which means that by the time the next wave comes in, it's hard to drain back the swash that entire distance. So for shallow slopes, it's really hard to drain that water back before the next wave comes. Whereas if you have a really steep slope on your beach, then it's quite easy. There's a lot of gravity pointing down slope, and it doesn't wash up the beach quite so far. So, I mean, that sort of very simplistic statement goes a very long way to explaining the difference between Beardmore and Rutford. So Rutford has sort of 3-meter tidal amplitude, and it's hard to drain back that 3-meter tidal amplitude given the shallow slope of Rutford, whereas Beardmore only has a 1-meter tidal amplitude. What's interesting, at least from my perspective here, is that another key variable is the permeability of the subglacial till, essentially the permeability of the beach sand underneath the glacier, as it were. And that, roughly speaking, is about the same in order to understand these two settings, which is remarkable because we don't know permeability of subglacial till to within orders of magnitude.
Great. Okay, we have a question in the chat. They say, what is the limit of CO2 we can pump into the earth without having an effect on the earth itself?
So there's sort of two ways to put that. So long as you measure things carefully enough, everything has an effect, right? So, so there is no amount of CO2 that you can put in that won't have some effect. The question is whether you can measure it. Do I have that slide here? No, I'll just talk to it. So it really depends on the setting. One of the things that I haven't mentioned here is pressure. So you might think, I'm putting CO2 into the subsurface, it's already full of water. Conservation of mass suggests that something has to give. Right? And the answer is actually, when we think about the Earth as being solid. It's not actually as solid as we think it is. So these same measurements of glaciers using satellite measurements that show vertical motions, you can see vertical motions associated with groundwater charging groundwater aquifers and discharging from groundwater aquifers, causing the land surface to go up and down subtly. And that is poroelastic in terms of its response. The Earth is responding a little bit like a sponge, and that is part of what would happen with CO2. It's a different question. In different geological settings, the reservoir, the porous rock in which you'd inject the CO2 might be larger or smaller, and then the pressure buildup could be either more significant or less significant. In the case that I showed you from Sleipner, so this one, the sand, which is 200 meters thick, is like beach sand. It's really permeable. There's lots of pore space, and it extends off for tens of kilometers. Is really, you will not feel that for quite some time. There are other reservoirs which are bounded by, for example, pre-existing geological faults that are more like 5 kilometers on a side, and those actually the volume of CO2 you can inject will be much more limited just because the pressure buildup. That's kind of why you need a lot of places that you can store it. And the other point that I'd make is that if those places are offshore, they're also conveniently under nobody's house, which is the other thing that often comes up as a worry.
Okay, yeah, that makes a lot of sense. Obviously, you wouldn't want someone's house being raised by a couple of meters over a period of time.
Well, you know, interestingly enough, your house will go up and down by tens of centimeters every day just because of the tides, right? That's the solid Earth response to the tidal cycle. So I'd argue that it, you know, even from a physicist, you should ask the question, over what wavelength is my house going up? You know, if your house goes up by 10 centimeters, but the wavelength is the diameter of the Earth, you really don't care. If your house goes up by 10 centimeters, but the wavelength is the diameter of your house, you definitely care. And so that, you know, you need a slightly more targeted question.
Okay, perfect. I wanted to also ask about the energy costs. You said, obviously, with putting the CO2 in the ground, you have to pump it, purify it as well. At what point does that become a detriment? Because obviously, if you're using energy, that's also coming from carbon emitting sources. So what is kind of the reasoning with that?
Yeah, so you know, the example, for example, here of extracting the natural gas, right? There's obviously an energy penalty associated with scrubbing the CO2 out of that natural gas stream. And there is no way that taking the CO2 out won't increase the cost. One of my grad students recently highlighted the following example, which I think is really quite poignant. He basically said, look, for concrete in the UK, for example, CO2 in terms of the making of the concrete is we emit a large amount of CO2 when we make the concrete. It would almost double the cost of the concrete to extract and store that CO2. So that's a significant cost in terms of the concrete. However, the concrete only makes up less than 1% of the cost of building the building. So actually, if we required all the concrete that we use in government buildings and non-government buildings in the UK to use clean concrete in which we'd stored the CO2, it would raise the cost of those buildings potentially by 0.5%. So obviously it makes a big difference to the cost of concrete, but maybe not to the cost of the building. And at the end, it's a societal question. How much, all options require some money. And I'd argue we need a huge array of options. Which ones do we want to pay? And I think, pleasantly enough, my sense is that people are willing to pay more money in terms of trying to find climate solutions.
Okay, perfect. Thank you. We have another question in the chat from Roshan. Are the extraction methods for the fossil fuels from this CO2 more shale-like or crude-like, or does it depend on where you inject it?
I'm not sure I quite understand the question. So the CO2 isn't derived from, well, so the CO2 is derived from all sorts of sources. It would be from burning of fossil fuels. It would be from burning of biofuels. It would be from industrial processes like the making of fertilizer or the production of cement. CO2 storage is then the question of what do you do with that CO2? Currently, almost all of those processes, we just vent the CO2 to the atmosphere. And the idea here would be instead you pump it down. If the question is related to my point about extracting natural gas, natural gas, when it comes out of the ground, has often a CO2 content. 10% is not atypical. Industry practice is to pull the natural gas and the CO2 out, and previous industry practice was just to vent the CO2. And that's why Norway instituted this $55 a ton tax on offshore emissions of CO2.
Okay, that makes sense. Just maybe more general question on what do you think the future of the field is? What research interests you that's up and coming? It doesn't have to be your own. Just where do you think climate science has got to go from here? What are the challenges it's got to face?
Yeah, so I think there's I'll sort of frame it in the sort of the two sides of my talk. I think there's still lots of interesting questions to do with how are both the Earth's climate and biosphere responding to climate change, and how do we understand that climate change more precisely going forward. I think, if you were a starting physicist now, in terms of understanding the response of climate change, things like aerosols, how do clouds form? That's a big area of uncertainty. Obviously, I think subglacial hydrology is important, but similarly, local predictions of sea level rise are going to be very important. In the UK, understanding flood risk and flood response, as well as periods of drought, those are going to be really important areas for us to understand, particularly as the climate gets more variable. So there's still plenty of areas where we need to understand how will climate likely affect our lives going forward. And I haven't even touched on some of the more biological responses or adaptations towards climate change. I think then on the other side, there's a huge number of more engineering challenges in terms of how do we decarbonize vast swaths of the economy, right? I think laying aside that I think a huge amount of our response to climate change has to come from social changes, we can make those easier or more possible by trying to rapidly deploy different technologies, anything from electrifying the grid to finding different fuels and methods for transport. Air is a really outstanding problem that still is rather difficult to solve. To how do we do things that are less, as it were, exciting, but possibly more impactful, like how do we thermally insulate houses better? How do we naturally ventilate so that instead of using energy derived from whatever means of power, we use the natural environment to ventilate our house. And even, in that sphere, the ventilation of houses and buildings also has implications for how do we ensure, interior air quality is as good as possible, which obviously after the last year is something that many of us are quite concerned about. So there's all sorts of questions from a physics standpoint. Where do we need to put our efforts? There's huge scope.
Yeah. Okay. Yeah. Obviously, it's a very expansive field and very interesting just hearing about your experience in it. How, just generally, how did you get involved into the field, and kind of what was your background, and how could any of us follow?
Yeah. So my own background, interestingly, is a bit of a wandering one. I started out as an engineering physicist in Toronto, so that was my undergrad. I then studied how sea ice forms and or doesn't in the polar oceans in a geophysics department. And then as a postdoc, I went to a maths department and thought about carbon storage. So really my interest had from the very beginning been how do you understand the natural environment? How do you understand how it responds both to changes, and how do you understand the patterns that you see in it? And that really was focused on environmental problems. And then in my postdoc, it was really using those kinds of skills to at least tackle one of the questions: how do we think about storing CO2 geologically? And that sort of approach has certainly stuck with me since then. I think, as a physicist, coming out of your undergrad or PhD now, you have so many skills to tackle so many of the outstanding problems in the climate sphere. It really is a question of where are your passions. There are any number of questions that we need to address, both in terms of more understanding at a local level about how climate is going to potentially impact our lives, and really asking questions about how do we make the most impact on those changes? How do we actually, how do you pick out the problems going forward in the future where changes that you can implement using your quantitative skills can really make a big difference? I think that's the sort of the key challenge going forward.
Okay, excellent. There is just a general question in the chat, if it was possible to get access to the presentation at all.
Yep, I can certainly send the PDF of the presentation over.
Yeah, okay, excellent. Thank you very much. If anyone has any other questions, feel free to ask them in the chat or on the Google form quickly.
We do actually have some questions in the Google form, so I might just go ahead and read some of those.
Yeah, please.
First one reads, thanks for the talk. Is there an obvious downside to CO2 storage that might explain why it hasn't yet been more widely implemented?
Two. There's the cost. It costs more, so that definitely is a challenge. And two, it's not as easy to get society behind essentially a waste disposal scheme as it is behind creating something. I mean, I think it's been a fantastic success that the UK has deployed as many, particularly offshore wind farms, but also onshore. And it, if you compare and contrast with the wind farm, you're selling a product. You're selling, I'm going to generate your electricity, whereas with CO2, you're basically selling a garbage truck.
Sure.
It's a little bit harder to sell the garbage truck, even though you don't want your garbage to pile up.
No, sure. I've got a question actually. What do you think, in your personal opinion, needs to happen for people to get behind CO2 capture more readily?
I think I think this is sort of tied to my point about what kind of problems could we do as physicists that would actually make a leading order difference. I think as a society, we need to really start thinking about strongly petitioning the government to really increase the regulations. That's one way to basically regulate. In my CO2 with concrete example, if you regulated the government to say, in the next 10 years, 50% of concrete that the government buys for its buildings needs to be clean concrete, that would make a huge difference. A carbon tax would also do it. Either, some sort of mechanism of regulation would make a huge difference, and would be, I think, more effective than relying on personal and public opinion. And I'm hopeful that public opinion has really started to gel and turn on climate change to the point where in the next, not as fast as we'd like, but in the next 5 to 10 years, governments will really start to change their tune in terms of regulations. But we've been hoping for a long while.
There's unless anyone else has any questions, I believe someone put their hand up at one point, so feel free to just put your question in the chat or in the Google form. But in the meantime, we have another question, which reads, can the carbon storage techniques be adapted for other greenhouse gases such as methane?
Absolutely. There's no reason why it can't. bizarrely enough, the requirements currently, certainly that were developed in the EU around the storage of CO2, require a fairly pure stream of CO2 to be stored. It's actually a bit of a limiting factor. If you could, within reason, put in slightly more impure CO2, that would be advantageous in terms of lowering the barriers. It would make the capture end less onerous. But yeah, in principle, there's no reason why you can't.
Thank you.
That is excellent. Okay, if anyone doesn't have any further questions, I would like to just say a massive thank you to you, Professor, and a massive thank you to all the attendees who listened in. It was a really engaging talk. I really enjoyed it. I just want to give a shout out to your excellent analogies. I thought the honey on toast one was very, very, very good. I really enjoyed that one. Thank you. I just want to share my screen quickly, just so that
Stop sharing.
everyone can see what we have going on next. So on stream A, we have Professor Martin Freer's Nuclear Physics and Energy talk. He is a professor at the university and also heads up the Birmingham Energy Institute. So he's going to have an interesting talk, similarly related, renewables, nuclear, things like that. So if you're interested in this talk, you'll probably enjoy that one as well. If you head over to stream B, we also have a LinkedIn masterclass. So that will also be very interesting and very good for any future career aspirations anyone has. So I'll stop sharing there. Just say another massive thank you to you, Professor. That was an excellent talk.
Great. Thanks.
Thank you. Goodbye, everyone.
Cheers.
There's a hand up.
You know what happens now? Do we just wait until people join the next one, or?
Yeah.
Yeah. Cool.
Professor Freer is already here.
Oh, yeah. And then I'll just switch off my camera.
Good morning. How are you doing?
Good. How are you?
Not too bad. So how's this going to work? You're going to push. It sounds like there's several streams, and you're just going to push me off into a stream somewhere, are you?
Well, yeah. This is the main stream, so yeah, you'll be speaking on here, I believe.
Okay.
I will make you co-host if you're not already.
Yeah, because I can't share my screen at present. So
Yeah.
presumably I've got to be able to share my screen.
Yes.
So Tom, the way it'll work is you'll just do some kind of introduction. Somebody will do an introduction, or
Yeah.
Okay.
Yeah, I think Henry's chair of this one, I believe. So he will. I'm just trying to figure out how to make you co-host. Sorry, for some reason it's taken the ability for me to do that away. So hopefully we can fix that in the next couple of minutes.
So I can share screen at the moment. So
Oh, you can.
Yeah.
Oh, okay. Okay, that's perfect then.
I've just hopped on. Is everything?
So yeah, it
sorted,
just
Tom?
literally just fixed. Yeah.
Okay, perfect.
That's okay. Thank you so much.
I'll go check on Stream B.
That's okay. Thanks.
Tom or Nicola, Julian here. I was just wondering if you have the sort of master slide deck so that you can just share a "we'll be back" or starting at 10, shortly slide for anyone arriving.
Yeah, I was just looking for it. I can't.
It's on the drive. It's not in a folder. I've just kind of left it. As soon as you log into the drive, it should be there.
Not Stream A or Stream B. It's just a separate option.
No, it's called Stream A.
Oh,
And then
okay.
it's got slides in it for each talk and a slide for break as well.
Slide. I can't find the slide for break, but should I just pop up the slide for?
Yeah, just pop up the slide for the talk. That's fine.
Cool.
Okay, so we are getting towards 11 o'clock. I think people can hear me. I hope people can hear me.
Yep.
Brilliant. Thank you. Sorry, we've got a bit of technical difficulties today. I'm also on Stream B on my other laptop. So I've got two screens, so I'm focusing on both. Despite the complications, I think I'll wait for it to go to 11, and then I will do the introduction for our next speaker.
And someone will have to give me captioning rights, please.
Yeah, who is the host? Because I think they have to add them as a co-host to do that.
No, it doesn't have to be a co-host, but just give me captioning rights through the participant panel. think Julian can do that if Julian is there. Thank you. I've got the...
Cheers. Thanks for the reminder.
Excellent. So we've reached 11 o'clock. So I think we're almost ready to start. I will start the recording. I don't have permission to record. So if whoever has the permission to record could please record it. Just to make sure that if people are missing it, they can come back and have a look. Thank you very much. Brilliant. It is an absolute honour to introduce our next speaker. He is Professor Martin Freer of the University of Birmingham. He is also the director of the Birmingham Energy Institute. Does a lot of work with nuclear physics, specifically light nuclei, and he won the Rutherford Medal in 2010, I believe. So be very interesting to hear what he has to say on nuclear physics and clean energy. So please feel free to take it away. Thank you very much.
Thanks very much, Morgan. Can you see my slides, and is everything working okay? Yep. All right. So thanks so much. Thanks for joining, everyone. Thanks for the invitation. So I've been given a slightly challenging title, which I've slightly twisted into nuclear science to clean energy. So it's almost a walk through from fundamental physics and how that fundamental physics can see the light of day in an application. And in this particular case, the application is, I will talk eventually about nuclear energy and what's happening in that sector and how it might play a role in the energy mix as we go forward. But what I'm going to do is start us off at the beginning, which is kind of going all the way down to our fundamental understanding of nuclear physics. And it's going to be done in pictures. It's hopefully not going to be too hard. There's going to be some twists and turns, which I'm hoping bring to life some of the things that you might have seen in your undergraduate programs. So where we're starting here is right back at the lightest end of the spectrum of nuclei. So this is the Segre chart. What you see is proton number running up at the left-hand side there. We've got neutron number clocking away on along the horizontal axis. And these squares here represent nuclei which exist in nature. And what I've put on top is some cartoons of different things. So we'll kind of build this up a little bit. So we've got the neutron and proton here. Our deuteron, put the two things together as it's here. As we might add to the deuteron a proton, we get to helium-3. And over here we would have tritium, triton, and triton's radioactivity decays down into here. The alpha particle, helium-4, is here. And then as we go along here, some interesting things happen. So helium-5 is black, it doesn't exist. Helium-6 has got a white square, it does exist, but it's got this funny pattern on top of it. These rings, they're called Borromean rings. And then we've got helium-7, which doesn't exist. And then we've got helium-8, which does exist, again, with some Borromean rings. The significance of these Borromean rings is that if you were to take any one of those rings away, then the other two rings fall apart. So you need all three components to be there in terms of these rings for the system to exist in its totality. And that's emblematic of the nucleus, such as helium-6. If you take a neutron away, you end up on this square here, and the thing falls apart. If you take an alpha particle away, you end up with two neutrons and the dineutron, which doesn't exist either, and it falls apart. So these nuclei here are called Borromean nuclei, and they have some really special properties. And the fact that you're just running along this edge here gives you a chance to really understand the details of the nuclear force. There's another, we'll meet some of these other characters as we go through. But there's another guy over here, which you can see actually turns out to be carbon 10. This is carbon 12. Carbon 10 just sits above this loop here, so it's kind of on a loop where there's two nuclei which don't exist in nature. So there's kind of a loop of stable nuclei, but two unstable nuclei. And so if we just switch to what carbon 10 looks like in this picture, so it's a Brownian nucleus. So this is actually taking something from the field of mathematics, where you have different kinds of knots, Brownian knots. And this is so the Borromean nucleus, Borromean rings is third order, this is fourth order. And what one sees here is 4 interlocking rings. And if you concentrate for a while, you'll realize if you remove any one of these rings, everything else falls apart. And that is the same with carbon 10. If you think about carbon 10, it can be made up of alpha particles and protons. And if you remove any one of these components, the whole thing falls apart. So these are really great nuclei to study because they sit right on the limit of stability, and they're bound, of course, by the strong force. By studying things right at that limit, you can get great insights into the strong force. So there's something to bear in mind as we go through. So this is going back to our fundamental understanding of how nuclei work. So the bit that we've just been exploring is in this part here. There is that ring, there's carbon 10. Here we can see get it right. So the helium isotopes, helium-4, helium-6, helium-8, and the deuterons down here. So this is a slightly unusual way of looking at the Segre chart. You can see it's on a logarithmic scale. And most of nuclear physics spends its life focusing on stuff over there, but increasingly what we're trying to do is understand how from fundamentals, so going down below the nucleon scale to the quark scale and the gluon scale, and indeed down to the QCD vacuum, how you can build up from those QCD degrees of freedom nuclei. And for a long time, we've not been able to do that, but right now is the generation where we can begin to talk properly about how to build nuclei out of those QCD degrees of freedom. So if we think about our fundamental building blocks, the proton and the neutron here, there's some surprises inside that may disturb us. If we were to look inside the proton, so here is an artist's impression which tries to depict what actually is going on inside the proton. So we kind of think the proton has got a couple of up quarks and a down quark, but actually inside it is much, much more complicated. You see, say, anything with a red line around the outside is an antiquark. So there's some antiquarks in there. So what's happening is that you're getting quark-antiquark pairs being born out of that QCD vacuum. They live and then they disappear back into that vacuum. You've got all of these gluons being exchanged between those quarks. And you've got, surprisingly, some strange quarks as well. So although we don't think about the proton having any strange quark content, it does, but it comes from the fact that you get strange, anti-strange quarks being born out of that vacuum. And we know that the proton is a fermion, so it's got spin 1/2, which is this big arrow here. But inside, you've got all of these spin particles. So quarks have got spin 1/2, you've got gluons are carrying spin 1. Somehow all of this stuff finds a way of giving you overall spin 1/2 for the proton, whilst having all of this kind of random fluctuations going on inside. So every time you measure the spin of the proton, it's 1/2, but somehow this dance of particles inside gives you always spin 1/2. And that's a bit of a mystery. So there is a spin puzzle, which is trying to understand how the proton gets its spin. And indeed, how does the proton get its mass? Because actually, the bare quark masses, quarks are quite light, whereas the proton's quite heavy. So where does the proton get its mass? And it's from all of this kind of complexity, these forces at play inside that proton. So some interesting things there. So that's inside the proton. If one wants to go to the next level, so we're now beginning to build these light nuclei. So we've got some forces between the proton and neutron and the deuteron. How do we understand those? And there is something. Well, if you've covered this in your subjects, you will know that at the nucleon scale, we describe those interactions through the exchange of mesons, pions, or short ranges rho and omega mesons. And there is something called a field theory, which somehow describes this exchange of this complexity of pions between the nucleons. And this is something called chiral effective field theory. Doesn't really matter, but you can see the pions being exchanged in different orders of complexity: leading order, next to leading order, next to next to leading order. So different ways and different combinations, different numbers of pions which can be exchanged between those particles, and that gives you that field theory. But something interesting emerges out of that virtual field of pions exchanged between those particles. And the something interesting goes back to the 2016 Nobel Prize. And that Nobel Prize was won by these three characters here. So David Thouless, Duncan Haldane, and Mike Kostowitz. These two, Mike and David, were professors, well, actually not professors, they were just normal academics at that time at the University of Birmingham when they did this piece of work for the Nobel Prize. This is a cartoon of what they won that Nobel Prize for, and it was one of those unusual ceremonies for the Nobel Prize where the person trying to explain what on earth the Nobel Prize was associated with had all sorts of objects, which included, I think, donuts to pretzels. But it was awarded for topology and the application of topology to physical systems. And so this is a cartoon from the Nobel Award. And what you see here is a lump of stuff which can be molded into eventually a cup, and that we should represent by the first step on this podium here. But as you can see with the POW, that cup suddenly gets a hole in some element of it, and that makes a difference. So you go from an object with no hole in it, it may have a dent in it, but it's got no hole in it, to one with a hole. And that gives you a step up, so you get a cup. So that is topologically different from that object now. And then you can keep molding this, and you might go POW again, and you get two holes, and that brings you to the next step. And that's topologically different from this object because it's got a different topology, and you just can't morph this into this without putting another hole in it. And then we got the pretzel, which is on the third step. And that is that's topologically different from this. And it says electrical conductance here because actually this was used to explain something called the quantum Hall effect, which you might have heard of. Now, in nuclei, you can do the same thing. So you can develop out of those pion fields different topologies of those pion fields. And this is something done through the work of Skyrm, Tony Skyrm, another great Birmingham physicist, mathematical physicist, and there's a group at Cambridge who kind of specialize in this in the modern day. But you can see those different topologies, so one skyrmion, two skyrmions, three skyrmions, four skyrmions, all the way through to 8. And you see one hole, you can see increasing number of holes as you create more sophisticated topological configurations. Now, the interesting thing that this group here at Cambridge found is that so this here would be one particle, proton. This would be the deuteron. This would be the helium-3 or tritium. This would be the alpha particle, helium-4. And that actually, if you were to take 8-particle system or a 12-particle system, actually there are topologies which look like this is an alpha particle, 2 alpha particles next to each other, or 3 alpha particles next to each other. So something really interesting has emerged out of that skyrmionic field, which begins to look like there might be those kinds of patterns that we saw back at the first slide. So I'm going to try and build up to an understanding of those patterns. So I'm going to do something really simple and actually stealing from undergraduate quantum mechanics. So what I've got here is a harmonic oscillator. So just think about it. I've got some parabolic potential here, and I've got a ball. A ball which oscillates around inside that potential. And all I'm going to do is make a nucleus by just dropping a whole bunch of balls inside this potential and see what happens. So there's 2 versions of the world. There's some balls over here which just been dropped inside a potential, and you can see that they oscillate in and they oscillate out again. Nothing very interesting. And the reason it's not very interesting is because they're not interacting with each other. If I had each of these had some interaction between each other, I'm going to create an interaction with potential. So this is some short range repulsion, some long range attraction. So this looks like a nucleon-nucleon interaction. You begin to get some really interesting things where you build up some correlations and particles start moving around together, and maybe that's associated with those kind of clusters that we saw inside that skyrmionic system. But if you're still with me, you'll be going, well, I don't quite believe you here, because the nucleus is a quantum object. It's not really fair to describe nucleons as particles. We know that at that scale, they behave as waves, and we would have standing waves inside a potential. And so we need a quantum approach to this, don't we? So what I've got here is the harmonic oscillator. And the harmonic oscillator is a solution of the Schrödinger equation for that system. So you've got the parabolic potential, and you're solving the Schrödinger equation. You get the standing waves inside that potential. And this is that solution. If that potential, so we're creating a nucleus, it's a spherical object if we've got a nice sphere. Now imagine for a moment we took that sphere and we deformed it, so we stretched it in one direction or compressed it in another direction. And then when we do that, oscillations along particular axes which become extended get lower frequency, so they come down in energy. And that's what we see here. But one sees some interesting patterns. So if you stretch this system to such that along this direction it's twice as long as in the opposite direction, then you get these are degeneracies. So how many particles you can put in each energy level. You can see that that pattern is repeated twice at 2 to 1 and 3 times at 3 to 1. And that is a piece of magic. It's a piece of magic because what it's telling you, out of those standing waves, you might get, so over here, so if this is the alpha particle, which it is, that you might get over at this point here 2 alpha particles, and over at this point here 3 alpha particles. And we can check that by calculating the density. What does the system look like from the wave functions? So here is, at this point here, I've got a dotted line associated with putting particles into this orbit. I got a dashed line from putting particles into this orbit. To calculate densities, you square wave functions and add the two things together, and you get something which has got 2 bumps in it. And then if you were to do it over here, you get something which has got 3 bumps in it. So for the 2 alpha particle system, you can see out of those standing wave patterns, you get 2 alpha particles. And over here for this would be carbon-12, 3 alpha particles. And this is, if you do those calculations properly, that's what you see. And over here is what happens if you were to take this system here, which is beryllium-8, and add 2 neutrons to it. This is a cartoon of what might happen to those 2 neutrons. So if you've ever played around with these things in a science museum where you've got 2 potentials and you put a ball in and the ball goes between those 2 potentials and it kind of goes in some kind of chaotic motion. That's what you would expect for this particular nucleus, beryllium-10. So where you can see that the neutrons, never sit still completely, but these neutrons move between one alpha particle and the other. So this is a bit like a covalent exchange of those neutrons between those 2 centers. So here is a visualization of what beryllium-11 might look like. So 1 more neutron, 3 neutrons whizzing around those two alpha particles. Those 2 alpha particles themselves are rotating. And here we've got those neutrons being exchanged covalently between those alpha particles. So it's, it's not our traditional picture, perhaps, that we might have grown up with in terms of what a nucleus looks like. But for these light nucleus systems, all sorts of exotic things can happen. Now, there's many extraordinary things in science, and for me, this is truly extraordinary. So this is, we sit here in whatever year we're in, 2021, with our understanding of physics and in this particular case, nuclear science. I'm going to wind the clock back to the beginning of the subject. Nuclear physics started, if you think about Rutherford, etc., started in the early 1900s. And this was a piece of work done by 2 people, Hastad, that you will have never heard of. Edward Teller, you might have heard of. He's the one who really stewarded the weapons program in the US associated with the atomic bomb. Before he was distracted by other things, he worked on understanding the light nuclei. And this is just his model, or their model. So these are predictions. So they didn't really know anything at that time. They just thought, could we use some simple ideas to predict the energy levels of nuclei? And the remarkable thing is, they pretty much got it right back in 1938. And you can see that as we march across the kinds of nuclei that they were looking at. So, things like beryllium-8, beryllium-9. So beryllium-9 would be 2 alpha particles and that neutron going between them, and carbon-12 and oxygen-16. So what their idea is that you can use very simple symmetries. So their background was atomic physics, and in atomic physics, it was known that you could use symmetries to understand nuclear atomic properties, and they applied it to nuclei. So imagine that I've got carbon-12. Here's their prediction here. That you've got 3 alpha particles, then it should have a particular symmetry, which is called D3H symmetry. So the 3 comes from the fact that there's 3 orientations of this object here. And the D is it's planar. So using that symmetry, you can predict a set of quantum states, and I'll show you how in a second. Other nuclei have got different symmetries. So this is 4 alpha particles in a pyramid shape. tetrahedral shape, and that's called TD symmetry. And again, they use that symmetry to predict the energy levels. Now it's okay predicting the energy levels, so they didn't know what the answer was, but it's then left to experimentalists to figure out, is it right? So here on the right-hand side is the experimental spectrum, and I got to try and see how this links together with the ideas of Hofstad and Teller. So you can see there's some color coding here, and I'll come back to that. But sitting in the middle here is a rather special state associated with Fred Hoyle. It's called the Hoyle state. And the reason it's special is because it takes a major role in stellar burning processes, the triple alpha process. So at the end of the life cycle of our sun, when all the hydrogen has been converted to helium, then what will happen is those helium nuclei will come together. They'll first make beryllium-8, and then you'll capture another alpha particle to make carbon-12. The Hoyle state is something that sits in that capture process and magnifies, accelerates the capture process by about 7 or 8 orders of magnitude. And so the reason that this is fantastically special is if this level wasn't here, you wouldn't be. And indeed, if I just start tweaking around in the second decimal place here, the world or the universe would be at an extraordinarily different place. So this state has to sit exactly the right energy, and has attracted a lot of attention in nuclear physics, trying to understand why is it this state has that energy? Is it sheer chance, or is it that the universe is being beautifully balanced to create the right conditions for life, etc. So what we're going to do is try and understand, based on Hofstad's and Teller's picture, how to build these nuclei. So take 3 alpha particles, and what we've been seeing is that those alpha particle system, they can rotate. Okay, so if they're rotating, there is an angular momentum vector. So it's orbiting, rotating in this plane here. Let's call that angular momentum K. But it could also have some rotation around this axis. And so coupling this motion and this motion, you get some kind of wobbling. So think about a coin spinning, and then it's kind of wobbling as it settles down on the surface. It's those 2 angular momenta together which give you the total angular momentum J. And this is Hofstad and Teller's equation, which describes that motion. So what you could have, first of all, is K equal to 0. And then you have rotation. So this J vector then just falls into this plane here, and you've got rotations of this object going around like this. Okay, and you can have different rotation frequencies, and that'll give you different quantum states. The next thing you could do is have each alpha particle moving around a direction perpendicular to the thing coming out of the screen with 1 unit of angular momentum, and 1 + 1 + 1 = 3. They've all got to be moving around. Otherwise, you don't get some chaos. So that would be K = 3. And then you get this state here, 3, 4, 5. So you would expect, just based on those symmetries, to get those quantum numbers. And then finally, you could let those alpha particles move apart, separate out the 3 centers, and then you get the same patterns again. So you get just like a 0, 2, 4, but you get another 0, 2, and 4. And because you've increased the moment of inertia here, you can see at the bottom, if you increase the moment of inertia, then what happens is the separation of the energy levels comes down, and hence it's all squashed. So what you might expect based on Hofstad and Teller's picture is 4 states quite close together. with with spin 4, angular momentum 4, but parities slightly different. So how does nature replicate that? Well, here is a truly remarkable experiment which was done in the US, which takes a gamma ray beam, it goes gamma ray beam of over 10 MeV. So how on earth can you make a photon of 10 MeV? So usually you would have X-rays or something like that. To get to 10 MeV is truly extraordinary. And the way that they do that is that you have a beam of electrons going really fast, and then you fire a laser beam to hit the electrons as they're traveling really fast. And the backscattering then of those photons is boosted from very low energies to very high energies by picking up the energy from the electron. So you can boost the photon energy by doing that to create very high energy photons, so of nuclear scale. And what can happen is that you can then take a carbon nucleus, excite it from its ground state, and pick your energy. So you can tune the energy of your photon to look for excited states. Oops, I'll just go back. So the excited state that this experiment was looking for is trying to look for this rotation of the Hoyle state. So here's the Hoyle state, and looking for that 2+ state there. And here is so a photon comes in, hits a carbon nucleus inside a big gas. You can actually track then these alpha particles as they go through the gas. There's the tracks. And then you can reconstruct the emission pattern. And here's the emission pattern. And then from that emission pattern, you can work out what the angular momentum of the state is. So what has been done is this rotation of the Hoyle state has been discovered, and all sorts of things have happened. And the Birmingham group have had an important role to play. So this then is our final picture of carbon-12. And so we have this idea of this rotations of the compact structure. So the 0, 2, and 4 that we saw from the Hafstad and Teller predictions. We've got the 3-, we've got the 4-, we've got the 5-, and then we've got a more extended structure, which is associated with the Hoyle state. And just as was required, we've got this 4+, 4+, 4-, all at the same energy. So the picture works, it's beautiful. So I'm going to try and transition in the last part of this presentation from actually, understanding from lots of different angles. So we kind of had that understanding of how you get there from fundamental forces and that pion field, the mean field of the harmonic oscillator, and then bringing that together with the dynamical symmetries in the experiment. So how do you transition from all of that complexity, and indeed my own personal story? So I spent many years of my life trying to understand all of that stuff, and that last half an hour has been an integrated reprise of all the things that I've done as part of my research career to nuclear energy. And at some point I decided that actually nuclear power and actually energy systems more widely were quite an important area, and I should spend some of my life studying it. So you will know that in the stars there is a colossal amount of energy, and in some stellar processes, so in supernovae and neutron star mergers and all sorts of other cosmic processes, nuclei and nuclear processes deliver colossal amount of energy. And if only we were smart enough to be able to capture that on Earth. Of course we can, but are we doing it in an optimal way? And what is the role of nuclear energy and nuclear power as we begin to develop our energy system as we go forward in the future? So this last part here is certainly less technical than the first part, so you can relax. So what this shows here is the point in time of 2008, which is an important point in time. It's when the Climate Change Act was put into place by the UK government. So UK, on the back of the Kyoto Agreement 1993, it took a little while to all of this to filter through, but decided to be world leading in terms of its commitment to decarbonisation, and committed at that stage an 80% reduction in CO2 greenhouse gas emissions. It's interesting to just look at how things have evolved with time, and one could wind the clock forward. You know, it's another 13 years since we decided to do something. But up to that point, this was the mix that we had. So it was a lot of fossil fuels. We had a lot of gas, and that's because we had the North Sea and relatively cheap gas extraction. We had coal reserves, but to this day we also import coal. We import a heck of a lot of gas as well now, as the North Sea is depleting, and indeed as we are depleting the amount of reliance that we have on coal. But nuclear, you can see, has been chugging along at a relatively moderate level since the 1960s, 1970s, when the UK developed its first nuclear power plant. The first one was at Calder Hall up on the Cumbrian coast. So, and here you can see hardly anything in terms of renewables. So this is all the renewable stuff, so wind, solar, etc. And our challenge has been subsequently to figure out how you go from a very high dependence, that's electricity, a very high dependence on our electricity generation on fossil fuels, to something which is less dependent on that fossil fuel base. But we must remember that energy is not just electricity, and energy is transport, it's heating, it's many things that run around the way that we manage our lives and devices that we use. So electricity is, so this is the whole energy system. Electricity is this red line here, which is kind of wandering along. And you see the seasonal variation. But the thing that should worry us a little bit is transport fuels is up here. And if we use gas as a surrogate for heat, heat is up here. So although we might have done some good work on decarbonising our electricity system, in the future, when we come to trying to manage an energy system in its entirety, we've got to figure out ways of decarbonising how we do heat. And that really is the major challenge that the UK faces at the moment. Just in terms of energy vectors or energy generation, this is again looking at electricity and how things vary as a function of time. So you can see the daily cycles here, and as we run through weekends, etc. And you can see how different sources of energy generation come online, come on stream at different times. So wind is blue, can't see it, but most obviously solar is yellow. And the thing that we're using at the moment to manage the variability in our energy system is gas. So gas is, well, it's flexible, but it's not particularly low carbon. So the real challenge that we have in the next step is how do you decarbonize the electricity grid by removing gas and manage the variability, and energy storage will have a role to play there, but also how do you generate additional electricity to overcome the fact that we've got to remove gas for heating as well. So that's where nuclear might come in. And what this shows here is the carbon footprint measured in grams of CO2 per kilowatt hour of different technologies. We're getting rid of coal. We're still relying strongly on gas, but we want to be shifting the spectrum of use or generation to the other end of the CO2 emissions. So this is kind of whole life cycle analysis of the CO2 emissions. So in the case of nuclear, it'd be, well, the CO2, what's the carbon footprint of extracting uranium all the way through to the decommissioning. So you can see nuclear is attractive, at least because it sits right at the end of that low carbon spectrum. So, you know, some interesting things here that you might say, well, you know, why is it that, for example, marine energy has such high, this is tidal energy. Why is that so high? Because typically there's a lot of concrete which is used in development of tidal energy. So what is happening? We know that we're getting very close to being zero coal on the grid. So a lot of coal power stations are being decommissioned. A lot in the region. So this is Ratcliffe over here near Nottingham. Rugeley Power Station had its cooling towers demolished 4 weekends ago. Places like Cottam in the East Midlands are also being decommissioned. So by the time we get to 2025, which is not too far away, we'll be without coal. We know that there has been a heck of a lot of investment in offshore wind, and that is really exciting because actually the cost now of offshore wind has come down extraordinarily, and it's a really efficient, cheap way of generating electricity, but we can't do that all the time. So how do you manage that? Times when you haven't got that generation. And then finally, what on earth is happening to nuclear? Well, these dots here are where nuclear power plants historically were around the country. We since those early days of the development of nuclear power have relied on 3 different types of reactors. A Magnox reactor, and there aren't any more operational Magnox reactors. The last one was operating in Anglesey. We had some AGR, advanced gas cooled reactors, and those still are limping along, but increasingly falling over. They're too hard to keep going. So they were built back in the 1970s. So they've kind of done 40 years worth of service, and we'll be left at a point where the only operating nuclear power station will be Sizewell B, which is a pressurized water reactor. So that's where we've got to in terms of existing plants. You will know that we are crawling towards increasing, or not really increasing, replacing the nuclear generation that we have in the UK. So Hinkley Point C is an absolute monster program. The attraction is that it's a twin power station. Each of these power stations here generate 1.6 gigawatts. That is about 7% of the electricity. So one power station will deliver 7% of the UK's electricity. The downside is that it's quite an expensive project. When it was first being touted, it was suggested it was going to cost about 5 billion. Now we're up at about 22, 23 billion. So it's they're complicated projects to build, but the potential is that it could operate for 60 years once you've built it. So it's kind of a reliable source of energy longer term for the future. Great progress has been made associated with the construction of Hinkley Point C. If you've been following the television program, you'll see that really extraordinary engineering feat. And you just look at the complexity of what is being done in terms of to create that power station. And there is a plan for Sizewell C, which is to build a similar power station over in Suffolk. What else is happening? Well, the UK is rather excitingly kind of nailed its colours to the mast. The UK government is funding a whole series of next generation nuclear programs. And those go from everything from advanced reactors. So advanced reactors take us to a point where we're doing things which current generation reactors don't do. So the PRISM reactor is an example of that. It's using fast neutrons rather than thermal neutrons, and it has this ability to take old nuclear waste and actually burn that nuclear waste and get rid of plutonium that we've got, plutonium stocks and things like that. So that's interesting for the future. But the other thing that the UK has invested quite a lot of money in up to now is small reactors, small nuclear reactors, not these big, huge things which you see at Hinkley Point C, but ones which might be able to go on the back of a truck. And the idea is that those reactors then get put inside some building. So it's Rolls-Royce that's developing this. You operate that reactor, and when it's finished its life, you put it back on the truck and take it back to the factory, and the factory delivers you a new reactor. And you can think what the attraction is there, that there's a lot of flexibility in being able to put your reactor wherever you want, industrial park, and get electricity on your doorstep, and there's also heat that you can extract out of the reactor. So interesting in terms of flexibility of the energy system. And then finally, this is something for the future. The UK has also funded a STEP program. This is the Future Fusion program, built around a UK design spherical tokamak, spherical plasma, and at present is seeking, UK AEA is seeking a site for this next generation reactor. And this list here, and you may be close to one, is a list of the 11 sites, I think it's 11, that have put a bid in to host this next generation fusion program. We've got a couple of places in the Midlands, West Burton and Ratcliffe, so that's in the East Midlands. So that's the thing for the future on the nuclear energy side. The thing for the future, which I must admit, I kind of ran out of time, from my own personal research perspective to properly understand. And that is, so I showed you how we can understand carbon-12 using these dynamical symmetries. The next step is to really understand how oxygen-16 works using the same principles, and some detailed experimental measurements which need to be done in order to properly understand all of the rotational symmetries that were predicted back in 1938 by Hastad and Teller. And with that, I will stop. I should probably stop sharing my screen. Can I do that?
Brilliant. Thank you very, very much, Professor Freer, for your wonderful talk. I think we're now going to open it up to questions. So if someone could share the Google Sheets link again, someone who's on the panel, that'd be brilliant. And in the meantime, I think maybe picking up on a point that you kind of mentioned earlier, could you tell us a little bit about how you got into nuclear physics and why you chose to do nuclear physics during your kind of undergrad and postgrad time?
Yeah, these things are always random, aren't they? So why did I get into nuclear physics? I did my undergraduate degree at Aston in Birmingham. We had a lecturer called Albert Bohr. And Albert was a nuclear physicist, and he brought the subject to life, and it really captured my imagination. Albert then ended up leaving the university and became leader of Birmingham City Council. So he kind of left the world of science for politics. But then what I did is I went to visit some of the UK's facilities. So up in Daresbury Laboratory, which is somewhere between Liverpool and Manchester, there's a place called Daresbury. There's a huge, now decommissioned, nuclear accelerator, and I went to visit it, and I just thought, I would love to do this. So it's slightly strange how these things work out.
So very much, I would definitely agree with the fact that having like an inspirational kind of role model or kind of something to aspire to in your lectures is quite good. Right, we've got a couple of questions in the Q&A box. First of all, when people hear kind of the term nuclear energy, it tends to kind of scare people. Do you think this could be an issue if nuclear energy was to be pursued and to put into practice as such a kind of great scale like you're advocating for?
So you're right that, or whoever asked that question is all right, that nuclear people worry about. I mean, it turns out that nuclear is actually, in terms of energy generation, the safest technology. Bizarrely, it's even safer that, you know, more people have died per kilowatt hour of wind than per kilowatt hour of nuclear. So there is a perception that it's extraordinarily dangerous, but actually the practice is that it's anything but. It's the safest energy generation technology. I mean, not to diminish the concerns that people might have around, you know, Fukushima. You know, Fukushima clearly had big impact. Actually, it turned out that the impact there was mostly sociological. So people's concern around, so that nobody died from radiation. People's concern around the potential for dying from radiation meant that you had all of this upheaval and the stress that creates. So there's no measurable impact in Japan around the emissions from Fukushima, and Chernobyl is worse in that case, but the numbers are still compared to natural cancer that you get from usual processes, conventional processes, compared to radiation induced. There's no measurable effect. So it's hard to say that. So the real issue is how people perceive risk, I think. So I think the fact that you had the weapons program and people think, well, a nuclear reactor can turn into a nuclear bomb is a bit of an issue, but it's not the reality.
Excellent, thank you very much. And I think there's another question that's kind of linked to the previous question on the Google Forms, and the question is, with sort of more advanced plants now, we're nuclear energy plants, are we in a place where we can control nuclear accidents better? And also, are we able to undo any damage to the environment if there is an accident?
Yeah. Yes, part of the reason that the EPR reactor that's being built at Hinkley Point C is so expensive is because now it's got safety system on top of safety system. The analysis that you can do around the probability of a failure of a reactor shows you that you're probably between 10 and 100 times more safe in terms of the present generation of reactors. So even though consequences of earlier generation reactors was not particularly significant, the risk of failure now is extraordinarily low. The kinds of, you know, what kind of cleanup do you need to do? I mean, these reactors are designed for a meltdown these days. So if the core melts through the bottom of the reactor vessel, and then there is something called a core capture, and so that's dissipated, and so you're containing things locally. The containment building of a nuclear reactor these days is designed that if a 747 was to fly at it, worst case scenario, and crash into it, then it would still be intact. So these they're built to extraordinarily high safety standards these days. I mean, the bigger issue is around waste and what to do with the waste. So yes, you know, you produce at the end of the life cycle of the operation of the reactor, the fuel comes out, you've got radioactive fuel, what do you do to it, do with it? At the moment, we're progressing in the UK with a deep underground storage facility. So that's the plan there.
Excellent, thank you very much. I think we've got one kind of final reactor question and then a couple more kind of nuclear physics theory questions. So we'll go to the reactor one first. What type of reactors are the modular Rolls-Royce reactors, and how do they work?
So it's very simple. It's a PWR, pressurized water reactor. It's just been miniaturized. So you have within the single thing, so you've got PWR, so you keep the water at high pressure so it doesn't boil, and you've got a two loop system. You've got the heated water, which is then through a heat exchange, creating steam, and that steam then goes through a generator, turbine, and all of that is inside that single module that you saw on top of on the back of the lorry. So it's not very adventurous, because that technology is used to power nuclear power submarines. So it's just taking that technology and turning it into a civil application.
Brilliant, thank you very much. We're getting close to the end, so I'll try and get through these questions on the theory quite quickly, and then I very much apologise we can't get to your questions because don't want to push into the lunch hour. When we look at nuclei as containing alpha particles, or being made up of alpha particles plus extra orbiting neutrons, are we able to have extra protons instead of the neutrons, or as well as, or is that something to do with the odd number of protons in the nucleus?
Oh, that's a brilliant question. Love it. So you could have, so what I described is alpha particles and neutrons whizzing around. You could have protons whizzing around instead. You can just substitute a proton for the neutron, but you have some additional repulsive energy, the Coulomb repulsion, because you've now got that repulsion between the proton and the protons in the alpha particle, and that ends up making it less stable. So these things are just kind of hanging on by their fingertips usually. And just putting that extra proton in is enough to push it over the edge of being stable.
Okay, thank you very much. I think we're going to finish there actually, because we're out of time. However, we would like to ask whether, if you're free this afternoon, Professor Freer, you'd like to join us in the kind of the Gathertown area to answer any further questions, or if people have further questions, whether they can get in contact with you in any way. So
I can do that. You just need to send me a link and a time, and I'll join and be happy to try and answer even fun questions.
That would be great if you could join us. In our program we have, so depending on when you're available, I know we have a few more questions left on the Q&A which people might like to ask you. We've got a lunch hour coming up now, and then at 2 until 3 we have sort of a networking careers hour. So if you're available then, that would be absolutely perfect.
I can do that. Just send me a link or tell me what to do, and I'll join you. Thank you very much.
Thank you very much.
So I believe now we're going to go to a lunch break. During lunch, you're more than welcome to join the Gathertown and just network with other attendees for the conference. And then following lunchtime, we'll have the keynote talk from Professor Petra Rudolph. So we hope you'll be able to join us then. There's also a lot of interesting things going on in Stream B to do with employability. I believe a CV masterclass. So if that takes your fancy, then feel free to join that as well. But in the meantime, really hope you enjoyed Professor Freer's talk. Thank you very much to him for coming along to talk to us. And yeah, enjoy your lunchtime, and we'll see you later. So long. Excellent. Brilliant. I think we're leaving this up on the YouTube for now.
Yeah, I think we're leaving the stream open just for the next hour.
and I need to go back downstairs to stream B to sort out that. So
Right, great.
I'm going to leave this one now. But yeah,
Okay. Yep. I'll stay in it. It's fine.
ta-ra.
Cool. See you later.
Hi.
Hi.
Hello, I'm Nat. I'm going to be chairing. Thank you so much for coming. It's an honor to have you here.
Pleasure.
Thank you. So I will obviously, first of all, just to make sure you know everything that's going on, I'll go through like the housekeeping stuff, letting people know they're muted, etc., and how to ask questions. And then I'll introduce you. So I just want to make sure I'm pronouncing everything right because I don't want to get anything wrong. So is it Professor Petra Rudolph? Is that how?
That's fine.
Yes. Okay. And Professor is fine. I saw you have like your Professor Doctor. That seems pretty interesting. So it's Professor.
Well, that's how we do it on the continent. So.
Oh, really? Okay. That's really cool.
If you have a PhD, it becomes sort of part of your name, the doctor.
Oh, okay.
So.
Yeah, I saw because I was preparing a bit and I was looking, so that's really interesting. I didn't know that. Okay. And also obviously I've got like loads of pages of notes here. So I'm just
well, you can cut 3/4 of what I said you just to avoid that you had to search on the internet for whatever you were looking for.
I mean, I did have a look at that email this morning. I was trying to...
I'm most proud of all the bachelor students and master students and PhD students that I have educated. That's the most important.
If you're most proud of that, I can introduce you by that if you want.
That's perfect.
Okay. Yep. Give me one sec. I'll just back up the email. Okay. Just scrolling down.
And as you have seen, I'll say a little bit about my movements around Europe.
Yes. Yeah.
Slide anyway. So.
Yeah, it all sounds really interesting. So we're really excited to have you here. So yeah, thank you for joining us. I also had a look and I was trying to work out what type of physics you'd like me to introduce you as because it looks like you do a broad range. It said experimental solid state physics, but then also
yes, exactly.
That's exactly
my specialty is surfaces and thin films.
Okay, obviously you will probably go into that. So I will mention experimental solid. I can't speak today. Solid state physics.
We can also say experimental condensed matter physics if that goes easier. That's the same thing.
Condensed matter. You know what? That might be easier because dyslexia on like 2 words with the same letter just goes over me. Condensed matter. I can do that. Okay, great. I think that is everything I need to ask you then. I'm pretty sure Tom is going to be supporting if anything happens. Oh, he's here. You're already here. Hello.
Yeah, I am here. Sorry, I'm just going to be eating in the background quickly,
That's
so I didn't get much chance. But yes,
okay.
it's really lovely to meet you, Professor.
Thank you. Very kind of you. I'm very happy to be with you today.
Excellent. We're all looking really forward to your talk, and hopefully it will go very smoothly.
Yeah.
Right, so I'll see you both later.
Yeah, that's fine.
Perfect.
So yeah, so Tom's going to be assisting. So if anything goes wrong on my internet, Tom can hopefully because you know how it's like. Oh, everything online is a bit difficult.
I have been all over the world in this last year.
Yeah, I bet you have. It's been an interesting year.
Well, actually, what I like best is that I've been also to places where I would be a bit reluctant to travel to, like Pakistan or
Yeah.
places in Africa and so on. But in this way, it's fantastic to be able to give talks and discuss with people, and especially
Yeah.
encourage young people not to give up, but to go for it. So
Yeah. I mean, that's been a positive of it being online, is we haven't had to as much just focus on as much as local areas. So, you know, so it meant we can just expand not just from Uni of Birmingham or just
exactly.
UK. So that's been really good. But yeah, so
Yeah,
yeah,
and
thank
I
you
think
for
it's also
joining.
great for people who are in places which are less accessible, and now
Yeah.
they can hear talks and assist and get the same information. So that's really great.
And I mean, we've managed to even have people who wouldn't normally be able to join CAPS because they're in other countries who've been able to, you know, listen along, join in, that kind of thing, or even like the other side of the UK where it might be a bit more difficult for them to travel down. It's kind of made it a bit more accessible in that way. So that's been quite good.
Yeah, nice.
Okay, so we've had the captioner join. I believe Julian will have to sort that out, but that's fine.
Yeah, somebody has to make me co-host so that I can share my screen, but that will be working out.
Let me see. I don't think I can do that. No, I can't. But hopefully, maybe Julian might be able to. Is it saying then if you click share screen right now, is it saying that you're not able to?
This will stop others sharing the screen.
Okay,
so
that's fine. You should.
I'm already enabled, but
yeah.
Yeah, it is fine. I had this problem with the previous talk, and yeah, as long as you can screen share, just because I'm screen sharing right now, if you can just overrule that whenever you need to, you should have all the privileges of co-host, because it doesn't let me make you co-host for some reason. It's changed, but as long as you can share, that should be okay.
Just try whether it works?
Oh yeah, of course. Go ahead. I can stop sharing.
Yeah, I can throw you out, you see. Oh, perfect.
Yeah.
Yes. Perfect. So
Great.
I go up again so that you can.
Yeah. Oh, or Tom can always overrule it again. It's no big deal, because we will have what will happen is we've got an introduction slide whilst I'm introducing you, and then you can just overrule it. And then once you've done speaking.
Now we know how it works. It's piece of cake.
Yeah. So yeah, Tom, if that's all right, if you can do the screen share at the beginning, so I don't have to stress about another thing. That'd be great.
It should be this one.
Yes. Okay.
So
brilliant.
we're here. That's fine.
All right. So we've got some attendees already in. Moment. So
which year are you of physics?
I've just finished my second year. So I'm still very early on.
Yeah, as have I.
Yeah.
Well, I decided in my second year that I was going to become a professor in physics. So it's the right time to make this kind of decisions.
I wish I could just decide that.
Well, that's how life goes. You decide what you want to be, and then you go for it.
Yeah. No, I'd like to try and stay doing physics for as long as possible, but it's really hard. It's hard. It's, just keeping going.
Why is it hard?
I don't know. That's a very good question. I think it just is innately hard. It's rewarding though.
Physics study turns your brain into something different than what it was before. Yes, but that's the fun of it. So.
Yeah. Is Julian here? Let's see. Not too sure. Yep. Okay. I will. Just respond to that.
There's a chat. Have you seen that? Yes.
Yep, I'm just responding now. I believe Julian has to do it. Yeah, Julian has to do it. So
very good.
I will just message a committee, see if any of them can get hold of Julian. Right. Julian is being sent this way as I speak. So hopefully he should be in a second to sort out captions and also to sort out the recording. Unless I don't know if Tom knows if we can record. I think Julian does it. And
yeah, Julian handles everything pretty much.
Okay, that's great. So we'll just wait for him. And then I believe we can probably get sorted.
Hi, everyone. I'm just bringing to a close the mini session in Gather, and we'll signpost people to join the 2 streams. We'll be going live in about a minute. Hope that's all right. Sorry to keep you in the dark slightly.
Okay, great. Thank you.
It's 1 p.m. and I see a fair amount of pop. I'll just give another minute just to let anyone who is
Fantastic.
lagging behind join.
All right. I'll bring the Gather session to a close now.
Okay, thank you. I'm just also going to put the Google form in the chat as well, if anyone wants to use that to ask questions. So that will always be there. So to everyone who's already here, we should be starting in a few minutes. We're just waiting for Julian's IOP talk, I believe, in Gathertown just to finish, so people can be sent over to both the streams, and then he just needs to start the recording and we will get started.
Okay, thanks, Nat. We are now recording and streaming to YouTube. Please proceed.
All right, thanks, Julian. So hello, everyone. Thank you so much for joining us today. So just before we start, so just a few little notices. Throughout the talk, you will be muted and your camera will be off. So if you experience any technical difficulties, you can use the Q&A box, or you can try and use the form, which will be put in chat has already been put in chat, but we'll try and put it in a few times. Tom, could you also go to the next slide for me, please? Thank you. So we will also be using this form, as it says on the slide, to submit questions, as well as the inbuilt Q&A function. So after that bit, I'd now like to say that we're very honoured to have Professor Petra Rudolph here to speak to us as our keynote speaker this weekend. So thank you very much. So she is a experimental condensed matter physicist, and she was the president of the European Physical Society in 2019 to 2021. And she has so far guided 34 master's students and 27 PhD students to their successful defense of their theses and supervised 23 postdoctoral research fellows. So thank you very much for joining us, and I'll let you take it away.
Thank you very much. Let me see if I can share my screen. Yes. Can you see it now?
Yes, I can see it.
So I'm delighted to be with all of you, and I have chosen the title "Carbon is a Girl's Best Friend" because actually carbon has had a very important role in my research activities throughout the years. But before I start, I wanted to tell you a little bit about myself. So I was born in Munich, which you see here in the center of the map. When I was 17, I moved to Italy, and I finished my high school at the German school there, and then I enrolled in physics at the Sapienza University. Then I specialized in condensed matter physics already during my studies. Then I started to work in Trieste, right at the border with Croatia, still in Italy. And from there, then I moved to the other side of the ocean and went to Bell Labs in the United States to do my postdoc. And then I started my academic career in Belgium, at the University of Namur. And 18 years ago, I moved to the Netherlands, to Groningen. So if you have kept on counting, you know that I have been working and teaching in 5 languages. That's what happens when you move around the continent, where people have all these different languages, but it's great fun. I like it a lot. So what I would like to do with you is travel to the nanoscale, because as you see from these images, until you really arrive at the nanoscale and you see the atoms, everything looks pretty much the same. And it's only there that things start to be really interesting. And just to get an idea of sizes as we go down, here is the nanometer scale, 10 to the minus 9 meters. And of course, you can go smaller. I stopped at the atometer, which is the estimated size of the electron. But those of you who are interested in high energy physics, of course, deal with particles that are even smaller than that. So to give you an idea of what the nanoscale really is, of course, 1/1,000,000th of a millimeter is something that you can write on paper, but I would like you to imagine it. So imagine that you are on a high tower where you look to the horizon and you can just barely see the curvature of the Earth. And that gives you a feeling of how big the Earth is. And then take with you a football and make the comparison between the size of the football and the size of the Earth. Well, the size of the C60 molecule, the Buckminster fullerene, is in the same relationship to the football as the football is to the Earth, approximately. So that gives you a bit an idea of how small this scale is that we are dealing with. So my specialty is surfaces and thin films, and I shall guide you through a few things which are interesting about surfaces. we shall start with the fact that surfaces allow the production of chemicals through catalysis. So essentially, what that means is that gases that would normally not react or react with a very low probability in the gas phase, they can absorb on a surface, they can split, and the atoms can recombine to form new molecules. That's, of course, chemistry, and it is what is used to produce all our soaps, all our paints, all our products from petrol, etc. It's an enormous industry. But I started my career with looking at processes like also the group of Gerhard Ertl, who got the Nobel Prize in chemistry for that in 2007. I looked at it a bit earlier, and what we studied this is the kind of machine we are studying it in, so that we study these surfaces in ultra-high vacuum. So because if you are not in ultra-high vacuum, but imagine you have a clean surface in your hand in air, it takes about 1 nanosecond for the surface to be covered with molecules and atoms absorbed from the atmosphere. So if you want to study it in controlled conditions, you have to work in these environments where you have the same vacuum as between the stars in the universe. And then you look how molecules absorb on the surface. And if you have molecules which contain carbon and you absorb them on nickel, for example, and then you heat it, already more than 20 years ago, we had something that we called graphitic carbon, and which we all now know by the name of graphene. But we did not care much about it because we had not understood how interesting it really was. So my group still is interested in catalysis, but what we do now is to look at things that are responsible for what happens in the sky. Namely, in the protoplanetary disks, there are lots of silicate grains. And on these silicate grains, there are many reactions which take place, which lead to the formation of all the molecules that exist in the universe. And what we try to do, two of my PhD students are working on that. We take the predictions from astronomical models of what the atmosphere in such a protoplanetary disk has looked like, and we reproduce it in our vacuum chamber, and we look what is forming. And indeed, we can see that different hydrocarbons are forming on our silicate platelets. Let's go to the next thing. Why are surfaces interesting? Because they give rise to very interesting electronic properties. So just to give you an idea of what that is, imagine a person getting up early in the morning and walking on his own on the beach. The fact that there are many people on this planet has absolutely no importance for the way this person is walking, and we can also describe the way he or she is walking very easily. If you instead think of crossing the floor of a discotheque, as I show on the right, the situation becomes much more complicated because all other people have to move if you want to cross the floor. But on the other side, you can also have new phenomena that you can't have on your own. Think of being picked up and passed on top of the crowd to the other side, or think of a Mexican wave. This is what we call correlated behavior, and this is what electrons can do as well. And then you get, for example, a superconductor. So correlated behavior of electrons is really fascinating, and that's something that I have studied a lot on fullerenes, so solids of fullerenes. So you take this molecule, which is formed of 60 carbon atoms, and you make a solid out of it. You can imagine like marbles in a box. And then between the molecules, you have these empty spaces, and you can fill these empty spaces with a certain number of alkali atoms. And what you see here is really, it gives rise to really interesting properties, because when you start out with the pure fullerene and you make a solid out of it, this solid is an insulator. With one alkali atom per C60 molecule, you get a very interesting behavior, which I'm going to show you in a minute. When you have 3, it becomes a metal or a superconductor. When you put a little more, it becomes a semiconductor. And when you put still more, it's an insulator again. So it's really surprising how the material changes when you just add a few atoms in the interstitial sites. So that was my first article in Nature. You may have heard that for a scientific career, it can be quite important to publish in this famous journal. And what we could do at the time was to show that the C60 solid with 3 potassium atoms per C60 behaves like a normal metal. And that was a big surprise at the time. And nobody thought that this would happen. So it behaves like a normal 3-dimensional metal. And then when you cool it down, it becomes superconducting. But as I said before, when you have just 1 alkali metal per C60, it's even more interesting. If you cool it from at high temperature, it's a strange metal, which means a metal with unusual properties. And when you cool it down slowly, the bonds develop along chains and it becomes a 1-dimensional metal. If instead from the high temperature you quench it down rapidly, you get the formation of dimers. And this phase is an insulator. Or if you cool it down very rapidly to very low temperature, you get a simple cubic phase, which is a metal. So this is what I mean with interesting electronic properties due to the correlated nature of the electrons. So essentially the electrons on the molecule and on the alkali, they feel each other and together they realize these different forms. What's also an interesting thing that you might want to consider is if I look at the solid, so here's the rubidium and the big balls are the C60, if I look at it through, I always have a layer of C60 below a layer of rubidium, then a layer of C60, etc. Now, normally in the bulk, you would expect that the C60 has taken up 1 electron and the rubidium has given 1 electron to the C60. The C60 likes to take up electrons. But if you look at that, you see that between the layers, you get quite a strong dipole because this is a minus and this, oops, sorry. I can't go. And the other one is a plus. So if you add up all these dipoles, you would get a very, very strong electric field, which would lead to an instability of the solid. So nature is very brilliant and solves this by reducing all by itself the electron density on the most outmost layers and having only 50% of the C60 which take up a charge and 50 which remain neutral. So that's a fascinating thing about solid state physics, is to see that the electrons all by themselves decide what they want to do and to study that. But let's go to something else. Surfaces are also important in determining adhesion and friction between solids and in determining how a liquid wets a surface. So you all have experienced that, I suppose, because you have been walking on ice, and at the temperatures at which we are normally in Europe, ice is very slippery. And that is due to the fact that the very last layer of water on ice is still liquid, and that gives the slippery character. It's just one molecular layer. If instead you go down to very lower temperatures, and that is what happened to poor Robert Scott when he went to the South Pole, also the last layer freezes, and then ice behaves like sand. It's not slippery at all. So manipulating the properties of a solid surface with just one layer of molecules is something very fascinating. And for example, we can do that by just putting something on top of a layer, which is only one layer thick, graphene oxide. And by this, we can change the temperature at which water freezes. This is important for lenses, because if you want to observe something in very cold conditions, you would like not to have to warm up your lens all the time. So that can be used for cameras, and of course also for airplanes. There are coatings in development which exploit this property of delaying the freezing onset. Something else is to change a surface with molecular motors. And the experiment that I'm going to show you is the following. You prepare a surface which is such that it repels the liquid. Then you come with light, and locally you change the molecules so that they are no longer repellent for the liquid, which means that the droplet will move there. And then because you have introduced this change with light, it is an excited state, which means that it will not live forever, but the molecules will return to their initial state, but the droplet has moved. So this is a way to move a droplet with light and molecular motors on the surface. So what were the molecules that we used for this? They are called rotaxants. They essentially consist of a staff with stoppers at the end and a ring, which can be in different positions on the ring. So what we are going to use is a molecule which changes its properties when the ring is on different stations. Now, you all know a surface which repels a liquid, and that's a Teflon pan. And the Teflon pan repels a liquid because there is fluorine on a Teflon pan. So we had this rotaxan made for us by the group of David Lee with fluorine on the staff. And then you have the ring, which binds to this group here. And when you come in with light, the ring moves over and covers the fluorine. So the surface changes from being not wettable to being wettable. That was the idea. And of course, with time, this ring will state will decay and the ring will go back. So this is how we realized that. What we do actually is to fix only the ring on the surface, and the thread is inside the ring, but can move. And then we start out with the fluorine exposed. So we have a hydrophobic surface, a surface which cannot be wetted. And then we come with the light that induces a chemical change at that station. The ring can no longer bind there. And so the staff moves, and at that point you cover the fluorine, and so your surface changes in properties. So let's see if it works. This is our surface, a droplet on the surface as prepared. You see that it is quite round, so it does not wet very well the surface. If instead we now expose the surface to ultraviolet light, and we wait a bit with the ultraviolet light on it, and then we put the droplet again. Look, the droplet is all flat. It wets the surface after irradiation. Now let's see if this is enough to move a droplet on the surface. So what I'm going to show you is a movie of the droplet after I have switched on the light. So let me just remind you what we want to do. We want to change locally the molecules here so that the droplet will move. Let's see if it works. Why doesn't it move? No. Well, what a pity. What you should have seen is that the droplet moves over here. Unfortunately, it doesn't seem to work in this PowerPoint presentation. So essentially, you can see it go, and we can also make the droplet move up. I saw something move. No. Okay. We can also make the droplet move up an incline. I have an image of that, which I can show you. This is the droplet in the beginning, as I just showed you. I switch on the light. The droplet flattens out towards the illuminated part and then moves because I have a difference in surface energy behind the droplet, where the molecules are not moved and not changed in configuration, and in front where they have been changed by the light. And this is enough to move the droplet. And these molecular motors are incredibly efficient. In fact, we can calculate the work that we have done against gravity in this case. And we can calculate that every molecular shuttle occupies a certain area. And so we have about 2 to the 10 to the power 12 molecules under the elongated drop. We can calculate that we need about half of the free energy that comes from the movement of the parts to do the work against gravity. And then we also are doing work against viscous forces, and that is approximately the same. So these molecular motors don't lose a lot of energy in heat, just like the natural motors. So what is important about this experiment is that we have shown that you can actually do work with artificial motors. And in the future, one could think of using such a principle to move very tiny amounts of reagents. So for example, you could think of a biochip, which is used to analyze your blood or your urine, and then you put the chip in your phone and the information goes to your doctor. So that's an idea. Nature uses molecular motors and switches all the time for all kinds of functions. Let's just see whether I can't start that either. No. Well, in any case, in your muscles, what happens is that you have very tiny molecular motors which all together do this kind of movement on a string, and by all the motors together, your muscle contracts. So the biological machines, as the artificial molecular motors, are very interesting because contrary to our motors, they use chemical energy, but they work at ambient temperatures and they are soft. They are made all by self-assembly. And because they are molecules, they are in movement all the time, Brownian motion. So you have to restrict in a clever way their architecture to make their movement go in the way that you're interested in. More about carbon. You can also make pillar structures. So the type of pillar structures that I'm going to discuss have a layer of graphene, something in between, and then another layer of graphene, as this temple is. So for example, you can put the C60 fullerene between graphene layers. And the way you do that is that you start out with a very thin slice of graphite, and then you pray the layers apart by intercalating, in this case, nitric acid. And then you expose it to the fullerenes and they go in. And the good thing is that you can heat just a little bit and the nitric acid goes out, but the fullerene stays in. And so you have this pillar structure. And you will say, okay, I have a pillared structure, which is like the Greek temple on the nanoscale, but what do we do with it? Well, we do a lot of things with it. We can use it, again, to have catalysis happen, because when you put molecules in a very tiny space, they behave differently. This is how our enzymes work. This is how many chemical reactions in our body work. They would not work on a flat surface. They work because the molecules are in a confined space. You can also use such a pillared structure to store gases in it. In fact, what you do is you design the pillars, not only that the pores have the right size, but they also have the right affinity for the gases you want to put in. You can do drug delivery, you can use it for nanomedicine. There are lots of uses. Environmental remediation, I'm going to show you a few that we have done recently. So there is this molecule, it's called chloridazone, and this is a herbicide that has been a lot used here in Europe in beet cultivation. The problem is that this herbicide stays in the environment for a long time, and under UV irradiation, it degrades into these other molecules, but they are also not very good for our health. So there is a need to eliminate these molecules from the drinking water, because they end up in the soil and therefore they end up in the water, and they are very small. So what one uses for that is graphene oxide. Graphene oxide is made from graphite just by attacking it with concentrated acids. And the nice thing is that in this way, not only you separate into very tiny flakes, but you also put these chemical groups on it. I'm not doing that, the chemists are doing that. What I have as a role in all this research is to collaborate with the chemists to characterize their materials with the physical means. And in fact, graphene oxide is a fantastic adsorbent for this herbicide, for chloridazone. You can absorb 67 grams per kilogram, which is really a lot. It's the same as what is used right now commercially to take chloridazone out of drinking water, but which is less sustainable, and that's activated carbon. So the way to produce activated carbon is less sustainable than to produce graphene oxide. So in the future, this will be used a lot. You can also think of drug delivery. This molecule, you have probably never seen it before, but what it is ibuprofen. So that's what you take when you have different kinds of aches. And the bad thing is that ibuprofen is very, very bad for your stomach, gives you all kinds of problems. So people would like to package it in a way that it does not come out in the stomach, but it comes out in the intestine. And we, the chemists I've been working with, they tried that out again with graphene oxide. It does not come out in the stomach fluid, but it comes out in the intestinal fluid. And so they are now exploiting that to make new drug delivery systems with it. So what do I love best about my job? Well, what I love best is the fact that when you think of an experiment, very often the results are slightly different of what you had thought they were. And then you sit together in the group of students and postdocs and me, and you think and you try to understand what you have seen in terms of results. And usually after some good long discussion, you get the explanation, you understand what is going on. And that is a fantastic feeling, because you know that in this very moment, you are the only persons in the world who have understood this particular thing in nature. And that is something that I like a lot. Another thing which I like a lot is to do what I'm doing right now with you, namely to tell the stories to other people at conferences or at workshops, because you see that very often people, when you start talking, they are not really interested in what you have to tell you. And then slowly they get hooked by the story that you have to tell, and they start to smile and they start to like what you're telling them. And that's something which I like a lot. Why I choose academia is because I love to be around people who think about in the same way about complicated things and about pasta. So people who can switch from very abstract circumstances to very practical ones. And you can do it in all of the world, as you have seen. And those are two facts which I think enrich your life very much. When I was your age, I never thought I would work with 3 Nobel Prize winners. And I also never thought that I would go to a Nobel ceremony to celebrate the winner. And this is 2018 with Donna Strickland. But what you will learn when you go into this field of physics as a professional researcher is that the world is very small, and you meet these people just naturally and you work with them, and it's great fun. So if you want any advice on how to have a good career, apart from liking it and being engaged, my main advice would be choose your partner well. So I married an artist, which is very convenient because you talk of other things than physics when you come home. And it is a profession that can be done all over the world. So moving is not a problem. A word of caution, this field, as many other fields, is not very kind towards minorities. You see that at the bachelor, master, and PhD level and postdoc, the amount of women in this case in Europe is increasing, or already when you come to the assistant professor level, it goes down. And when you go higher up, this is really opens. So it's getting better. I have seen important improvements all over my career, but the problem is not solved yet. So if you belong to any minority, of course, the biggest minority are the women, but there are many other minorities as well. You will probably feel other people's unconscious bias in one way or the other. A very interesting interview in that respect is the one that was published in Nature in 2006 of Ben Bars. Ben Bars is a biologist who used to work in Stanford. Unfortunately, he died a few years ago, and he changed sex. And shortly after he changed sex, a faculty member was heard to say, Ben gave a great seminar today, but then his work is so much better than his sister's. Of course, he doesn't have a sister. So that's something you will have to fight with, but never give up. I think the future is bright for young researchers in physics, and I wish you lots of success. And the very last thing I would like to share with you is the statistics from the United States. But the same is true in Europe. I just haven't been able to find the numbers. So this is the average salary premium for people who have studied a STEM subject. And it is 12% for men and 9% for women. So men who study STEM subjects, no matter what job they do afterwards, they have a 12% higher salary. If they not only study a STEM subject, but they also work in science and engineering, they have a 23% higher average salary than other people. For women, the advantage is even bigger. If they have studied natural sciences or engineering and they stay in that field for their work, they have a 29% higher salary than other people who have made other choices. So I would very strongly recommend that you keep these numbers in mind also when you make choices. That was all I had to tell you today, and I thank you very much for your attention.
Thank you so much for that amazing talk. I really enjoyed it, and I'm sure all of our attendees did as well. I'm just going to, or hopefully Tom may repost the Google form in the chat. So therefore people can ask questions that way. And we also have a Q&A here in Zoom as well. And we will get through as many questions as we can. I'm just, I think Tom, okay, I'll just send it here. So you should be able to see that form now. Okay, so we've first of all got a question, an anonymous question, which said, do you have any advice about being a woman working in physics? I sometimes find it hard to be taken seriously compared to my male peers. And as someone about to begin my PhD and then wanting to continue in academia, I worry about losing out on opportunities due to being a woman.
I would say unconscious bias is unfortunately something which pervades our society. So it is not men against women, it is society against women. Everybody has it in their brain, and we all have to realize that it is there. However, luckily in the last years, and when I say the last years, I mean approximately the last 20 years, there have been a lot of initiatives to be aware of unconscious bias. And so on one side, one tries to encourage people to not to be dissuaded by the fact that unconscious bias exists. And on the other side, one tries to mitigate its influence as much as possible. So for example, at my own university now, everybody has to go through unconscious bias training before being on a committee that decides on people or decides on money, so that you realize what your brain is doing, and therefore you are less influenced by your unconscious decisions, but you make your conscious decisions prevail. So the situation is getting better in this sense. Of course, one also has to defend themselves, and yeah, on some occasions you get people who say stupid things to you, but you mustn't take that too seriously. I mean, be above, get a good elephant skin, and everything will be fun, and fight for the important things. So every now and then it's important to pick up something that is really goes wrong, and then to fight that it's done in the right way. And I have done that all my life. So
thank you for answering that question. That was a great answer and very inspiring. So we got a very different question here from Vic, which says, can you target specific frequencies for surface sensitivity?
I don't understand exactly what you mean by that. One can structure a surface for having particular optical properties. So, for example, if you look at the frames of glasses that you wear, sometimes you see that they have funny colors, and that's not paint. That is actually a physical effect of interference of a thin film. So one can structure a surface. That's also why beetles are, for example, iridescent. That's also just a physical effect and not the effect of pigments. So yes, you can make a surface sensitive for particular frequencies by nanostructuring it.
Great, thank you for answering that. We currently don't have any other questions. So again, if you would like to submit a question, the link is in the chat, or you can use a Q&A here in Zoom, and we'll see if we get any more from anyone else.
I have a question, if that's okay.
Go for it, Tom.
I'd just like to ask, what, in your opinion, is the most exciting use of carbon, or specifically graphite, in the future, and any of your predictions on the biggest technology that it will be influenced by?
It's very difficult to say one thing, because we are discovering so many things of carbon. Now, the fantastic thing of carbon is that it is light. Graphene is has very particular heat conduction properties, and that has to do with how the electrons interact in a sheet of carbon. It conducts electricity in a phenomenal way, much better than any normal metal does. It's also impermeable, so you can realize all kinds of devices where you don't want certain gases to go through, and you can realize special environments which mimic environments that we have in nature, which are very constrained, and you make entries for reactants, and then you let them react. You can create very particular electronic properties, by the way, how you put sheets together. So just one sheet, or just two sheets only of carbon, or carbon with something else that interacts, so where the two layers interact, and you get the most curious properties, a little bit like I showed you with the fullerenes. You can do it also in 2D. So you can do it also with flat sheets. And we are just starting to understand that, really, how to do it and how to describe it. And so there are going to be tons of things coming out in the coming years. The great thing is that carbon is so abundant. So it's not something, I mean, you have to think that in your mobile phone, for example, right now, there are lots of elements which are either getting scarce, or they come from war zones, so like cobalt or these things. And we don't really want to finance wars with our need to have efficient means of communication. So it's really crucial that we work towards understanding the physics of these new combinations of materials, especially with carbon, because then we can produce it everywhere. We can replace what we are using now with new devices that are much more sustainable and that are better. So
great, thank you.
We have another question here, and it's asking if you have any advice to physics students who would like to study or research across Europe and the wider world.
Well, essentially, right now, you are in a very lucky period, because there are many more positions available than there are good candidates. So the important thing is that you have the courage to move, because the good position might not be in the same town where you have grown up or where you have moved to study, but might be in the other side of the globe. So it's fine to move there. Of course, all these things also require a bit of logistic combinations. As I said, to have a partner who can move with you is something which makes life a lot easier. So that's something to consider. What you should also consider in the future is if you have already partnered up with somebody who does the same things as you do, try to diversify the things that you study, because hardly any university can take two people. At the doctorate level, it's not a problem. At the postdoc level, it's not a problem. But later on in your career, hardly any university can take two professors who do the same thing. It's just too expensive. You only have so many positions, and you don't take two people who do the same thing. So if you have a partner who does the same thing as you do, it's wise to diversify and to do slightly different things, so that you are then interesting for a university to be both hired in the same place. That's just an idea for the long-term view.
Thank you for that. That's something I definitely wouldn't think of. So that's really interesting to hear it that way. We've also got another question here from a question and answer, asking if using too much carbon would be harmful for our environment, and how we can make sure environmental pollution, make sure environmental pollution at the same time using carbon. So first bit is about whether it be harmful for the environment. I don't know if you want to.
Everywhere you look, there is carbon in this world. So I don't know what you mean. It is harmful for the environment. It is there and we can use it. There are certain types of molecules which can have a negative influence on us, and they are very often specific hydrocarbons, very often in combination with fluorine or with other other atoms that can have a bad effect on us. So that, of course, has to be avoided, but you saw also that you can use the carbon itself to eliminate such molecules from the environment. So it is a very good way to use what we have abundantly available and to clean up what is out there. So we have become a lot more conscious over the last years of how superficial humanity was in treating the environment, and we are all looking now very strongly for solutions, and physicists can have a role there in helping the material scientists to develop certain materials that can be used. And of course, we also have to check whether things are negative for us, because a nanoparticle always has different properties from the same element in a macroscopic form, because a nanoparticle has a lot of surface and surfaces are reactive. So we still have a lot to learn on everything that we use, and we have to avoid using things that really become dangerous for us, that's for sure. But carbon is pretty good in that. So you can, that's why you can use it also for drug delivery and for things like that, because it doesn't really harm you.
Great, thank you for that answer. And also thank you for that question. It's really interesting to think about environmental impacts. Another question here. So they were saying that trying to cool graphene to sufficiently low temperatures so that it enters its superconducting state comes at a considerable energy and financial cost. Do you think there will be a way to make this process more efficient so as to enable graphene technologies to be used more widely?
Well, yes, because we are starting to understand. So first you discover such a correlated state, and it happens at a very low temperature. So that is not technologically interesting, because if you want to use superconductivity, for example, in the windmills or in things like that, as we are using it now, and you want to use a cheaper material or a more sustainable material, it must not work at too low temperatures, but you have to increase the temperature where it turns superconducting. And for this, we have to study these systems and really to understand the process. So for example, what we have understood so far already, that sometimes stretching has the same effect of rising the critical temperature. So that is right now things which are only predicted theoretically, that if you find a way to stretch graphene uniaxially and you put some lithium on it or some other alkalis, it should have a much higher superconducting temperature. But we have yet to figure out how to realize that experimentally. So this is how it usually goes. Somebody makes a modeling in the computer and tells you, okay, if you do this, you should see that. And then sometimes one figures out how to do it, and one sees the thing that has been predicted, or one sees something else. So for example, with magnesium diboride, it was predicted that the superconductivity should increase tremendously when the thickness of the film was very small, and then we tried to measure it and we didn't see it. So we went back to the theoreticians and we said, hey, look, our measurements are good. It doesn't do what this paper predicted. And then they did another calculation and they found out that actually the surface electrons, which had not been considered in the first model, had a very important role and influenced it in another way. And then they went on and they calculated that if you stretch it, the temperature should go up. So you go in this way, you go in small steps where you have a theoretical prediction, and as an experimentalist, you try to check the prediction, and very often you'd find something different, and then you try to understand it together and so on. And that's how we proceed. And that's the fun of it. So, yeah.
Thank you for that. We only have time for a few more questions. So the next one here is, could you speak about your view of Moore's law with silicon and the future of graphene as a possible solution?
Well, as we make devices smaller, we are now going into the regime where the quantum mechanics goes in, and so where the properties really fundamentally change. So the way that a macroscopic device functions is not the same that a nano device functions, a nano-sized device functions. So that means that you have to find a way in which you make a nano device which has the same functionality as the macroscopic device that you are trying to replace. And that's what people are working on right now. But we are also working on very fundamentally new things. So for example, your brain is a formidable computer which uses far less energy than any computer that we use in our devices. And the main reason is that the elaboration of the data and the storage of the data are not in two different places, but they go together. So you don't have to exchange information with the storage to do the operations on your data. And that's what your brain does. And what we are finding out right now is that you can reproduce that with inorganic substances that show the same behavior as your neurons. This is called neuromorphic computing. And that is things that people are studying. My group is studying that as well. I have 2 PhD students who are working on this and who work with tiny clusters of gold that contact each other in a totally disordered way, and that show a conductivity which can be switched and which shows the spiky behavior just like neurons. And we are right now studying this and trying to understand how we can make devices with it and so on. And of course, my group is not the only one. There are lots of groups all over the world who are studying this, but we are really moving towards new concepts to realize computation. The quantum computer is another approach. So we are trying to use other approaches to do calculations with devices that are more sustainable than what we have now. Just to give you an idea of how terrible our current computers are in terms of energy consumption, 10 Google searches, 10, is the same energy as boiling a liter of water. Yeah, so that just gives you an idea, okay? So you understand immediately that we have to do something about it.
Well, that was quite an amazing fact. I didn't realize that. I think we only have time for one more question before we're going to have to finish up. So the next question we had was that you talked, well, in your talk, you mentioned a lot about the coordination between fields of chemistry and physics. What do you think about the cooperation between physicists and scientists in other fields? And is this going to become more important in the future?
Well, we are very often working in multidisciplinary teams. If you continue your work in the industrial sector, you will see that essentially all of you will work in multidisciplinary teams. In the university, it depends on what kind of physics you do and what your specialization is, but it is very common to work together. So for example, with these gold clusters to understand how the conductivity works and so on, we work together with mathematicians and with information scientists who are computer scientists who make models for what we observe. And they compare it to the models that are made for brains and so there is a lot of interdisciplinary collaborations. Of course, you have to learn to understand the language of the other one. It took me about 5 years to really understand what the chemist means. So it's something that takes time, because people mean different things when they use the same words. And also the fascinating things of a physics study is that you end up with a fantastic brain, which is different from the brain of people who have done other studies. And so you think in a different way, which is really great, but it also means that other people don't think like you. And so you have to understand how the other people reason when they think. And that takes some effort, but it's something which enriches your life. So I'm very happy about it.
Thank you for that. And so we're going to finish up now. So thank you so much, Professor Rudolph, for speaking to us. It was an absolute honor to have you here. And thank you for answering everyone's questions. Thank you to everyone who has joined and listened in and also submitted questions. It's been really great, and we've had some really good questions. So thank you for that. So next we will be having a careers and networking hour on GabbaTown. And then later on, we'll get back into some more panels and workshops. So potentially I'll see some of you then. So thank you for coming.
My pleasure.
And also, Professor, if you'd like to join back at GabbaTown,
I'll come
you're more
to
than
the
welcome
GabbaTown
yeah, you're more than welcome
if
to.
anybody wants to talk to me one-to-one, just find me.
We did have a few questions which we didn't fully get through, to be fair. So you never know, you might get some ones that we've got here.
Very good.
Thank
See you there.
Thank you. Bye.
Thank you.
Hello.
Hello, how are you?
I'm good, thank you. Just connected 5 minutes earlier as per instruction.
Brilliant. Thank you very much. I think we're just going to wait for people to join because there's a bit of a networking event going on in the main kind of
Of course.
space.
I just testing my video and my sound, if you don't mind, just so then everything is in place.
Of course, no worries. If you need anything, just let me know and I'll try and get the relevant people in to...
It's the volume okay, or am I too faint or too loud?
I think it's fine.
Okay.
Yeah, no, you sound fine. Hi, I'm Tom. I am also
Hi.
here to help.
Okay, thank you. So yeah, I think I'm all right then. Okay, I will switch on the video at the right time when you instruct me.
Perfect.
Who's the moderator?
I am.
Okay, hello then, again.
Potentially worth asking. Are there any questions you'd like me to ask?
Well, let's see how it goes. I know Victoria very well, so we can have a chat and we shall see. But yeah, it's just a panel of two, right? Victoria and I.
Yes, I believe so.
Yeah. Okay. Is it recorded?
Yeah, it'll be recorded and streamed on YouTube. I think we're live actually right now.
Okay, hi everyone. We are starting to move towards the start time. We're just going to wait for everyone to be able to turn up. We're also waiting on a panelist at the moment, so thank you very much for your patience. In the meantime, if you want to be ready to ask any questions to our panelists, you can see the Google form link in the presentation. I should also be able to copy and paste that and send it to everyone in the chat. Is it TYK9? Yeah, it is.
Hi everyone, I think we are going to go live shortly. So I've made the captioner able to caption, and once, if you give me the signal to start the recording, I can then press go and you're welcome to proceed.
Excellent, thank you very much. We are just holding on for, I think, one more panelist, and then we will see.
In which case, I'll go and let Stream B know the same stuff. Thanks.
Thank you.
Hopefully, Professor Martin will be here soon to join us. So thank you, Christina, for joining us as well.
Thank you for inviting me. Hello, everybody.
Whilst we wait, I think I will do the housekeeping announcements now, just so that when our second panelist arrives, we can just go straight into it. A couple of things. If you've been to any of our talks so far, you'll know that you're unable to turn your camera or mic on if you're not a panelist. However, you are more than welcome to submit some questions through the Q&A. Please use the chat sparingly. If you do have a genuine problem, ask it through the chat to the panelists, and either myself or Tom will help you out. If you want to ask anonymous questions, please follow the link to the Google form, which has been shared. And yeah, this panel will be Q&A style rather than a presentation talk. So the more interaction through the forms we have, the better. I think that's pretty much it. Other than we hope you're having an enjoyable day here at CAPS 21. And I'm sure you'll carry on enjoying it because we've got such good things scheduled this afternoon. I've really been looking forward to the particle panel, so it should be great fun. We'll just let the stream of participants just kind of stabilize, just so we're not missing anybody, and then I think we'll aim to kick off at about 5 to 10 past, just to allow our second panelist, Professor Martin, to have enough time to join. Thank you very much. Tom, would you mind bringing up the CAPS slides, please? Thanks. Okay, so in the interest of time and not wanting to mess up the schedule anymore this afternoon. I think we're going to kick off with just Professor Lazzaroni, if that's okay. So if you would like to introduce yourself, tell us a little bit about how you came into particle physics and maybe a bit about where you work. That would be excellent. Thank you.
Yes, so good afternoon, everybody. My name is Cristina Lazzaroni, and I am a particle physicist at the University of Birmingham. And so so how do I come to particle physics? Well, that was a bit of time ago, but essentially, at secondary school, I decided that I enjoyed very much sort of understanding how things work. And so also another thing that I really liked was the opportunity to travel. And so I thought I could combine my my passion for science and understanding how things work at primarily fundamental level with travel. And so that's how I chose physics and particle physics. I just see that Victoria is in.
Hello everybody. So sorry. It's the usual Zoom problems, and my laptop's also in a really bad mood, but I'm here now. I'm sorry for being late.
Hi, Victoria.
Hi, Christina. Christina and I know each other from a long time ago, so it's really lovely to be on this panel with her.
Brilliant. We ask that to avoid any kind of feedback with the audio, that if you're not talking, to turn your mics off, please. That would be great. Thanks. We've just started, Professor Martin. Thank you so much for joining us. We just kind of kicked off with introductions for with Professor Lazzaroni. So if you would like to introduce yourself and tell us a little bit about how you got into particle physics, that'd be great. Thanks.
Okay, yeah, so my name's Victoria. I did my undergraduate degree in the University of Edinburgh. This will become a theme. I started in 92 and graduated in 96. And back then we were the last year in Scotland that couldn't do like a master's, combined master's degree. So I've just got a bachelor's. Everyone younger than me, typically before they do a PhD, will have like an MPhys or an MSci degree. And in the last year, I went up and spoke to the professor who was teaching us particle physics. There was 3 guys in the class, because it was at 9 o'clock. The lectures were a bit kind of random and haphazard. And I said, I really like this. Do you think I could do a PhD? It doesn't work as easily as this nowadays. And he said, it was Professor Ken Peach, that at least Christina will know. He said, okay, Victoria, I'll go and think about it. And he came back the next day and said, yes, probably. Let's interview you. And eventually, after some kind of due process, so it wasn't all just in the background, he said, yes, we've got you a place. So I stayed on at the University of Edinburgh to do particle physics. Now, originally I'd been a theorist, so my undergraduate degree is in mathematical physics. And I went over at that point to experimental particle physics. And the great thing that still happens to students to these days, if you do experimental particle physics, is you get sent to CERN or wherever your experiment is. But typically the experiments are at CERN. And actually that's when I met Christina, because Christina was a researcher in the same group. So she was also working for Edinburgh. I was just a PhD student. She was the postdoc. And I worked on an experiment there. I don't know if Christina mentioned it already. It was called NA48. It's not a very sexy name. It was the 48th experiment in the north area at CERN. And we were looking for a very tiny difference between matter and antimatter, between one kind of kaon and its antiparticle. And we managed to see it. It's a very small, subtle effect. It's a 1 in 2000 effect in a 1 in 1,000 effect, which these days doesn't sound very much, but back then it really was really hard to see that. And so we saw that. And when I was, sorry, this is my whole life story. I don't know if this is what you wanted, but when I was doing my PhD, I met a really enthusiastic researcher at CERN called Maida Velasco. And when she was at CERN, when I was at CERN at the same time, she got a position as a professor in America, so kind of lecturer stage. And she said to me, Victoria, you must come with me. She encouraged me to apply for a job at the university that she was going to, that was open already. So, I mean, the job was open, but she was like, no, you apply for this job, please, Victoria. And so I did. And I got that, perhaps with her recommendation. So I moved to the States for 5 years. This was in 2000. And I remember, so I went to the States in August 2000 to Chicago. And I flew back in December for 5 days to graduate with my PhD from Edinburgh. And then went back for 2 weeks and then went back to the UK again for Christmas and then came back. So there was quite a lot of flying. So my postdoc, I was based at Northwestern University, which is just outside Chicago. But the reason it was really good to be there at that time is I went to work at the Tevatron, which was a collider at Fermilab, which is also just outside of Chicago, but a different just outside of Chicago than where my university was based. But that was great. So I typically spent 2 or 3 days a week at Fermilab and 2 or 3 days a week at the university, which I found was a really nice balance between being involved in university life and also being involved just with all the other researchers. So I did that for 5 years, which back then, at least your first visa to go to the States as someone with a PhD ran out. And I decided I wanted to come back to Europe. And it just so happened there was a job in Edinburgh at that time that I applied for and I got to be a lecturer. Now it shouldn't sound that easy. I applied for 9 jobs at that time, some to be postdocs, some to be academic staff, faculty, and I just happened to get the one that was in Edinburgh, so it wasn't super easy. So that was 2005. I'm sure I sound really old now, and I've stayed in Edinburgh ever since. So I was appointed as a lecturer, and then I became a reader, and finally 4 years ago I became a professor. So what do I do in Edinburgh? So when I started, I was working on a project that's still exists, but not very much has happened. It was called, or is called, the International Linear Collider. And the idea is to collide electrons and positrons, anti-electrons, and do what a collider does, make particles. We were hoping, back then when we were thinking about it would be good for looking at Higgs bosons, and indeed, now we've found the Higgs boson, we know that idea is a good idea for looking at Higgs bosons, and recently people have started thinking about it again. It would probably be built in Japan. But because that project wasn't going so well, in 2008, I joined the ATLAS collaboration with some of my colleagues in Edinburgh. So the ATLAS is one of the experiments at the LHC at CERN. So I'm sure you know a lot about it already. But just as a reminder, we get protons, we speed them up to 99.9999999% of the speed of light, batch them together, and ATLAS literally just watches what happens in those collisions and tries to pick out the interesting things that happen, including the Higgs boson. And that's the thing that I look at the most actually these days. Okay, so that's my long story. That's my whole biography.
Brilliant. Thank you very much. That was really, really interesting. I think we didn't cover this with you, Lazzaroni. So
yeah, maybe I
can.
Yeah, exactly. Maybe I can. So actually, for me, yes, I mean, at the university, I wanted to do something about physics, but I happened to go into particle physics a little bit by chance. I found all physics at that time extremely interesting, and in fact, I wasn't so entirely sure I was going to be an experimentalist. I studied in Italy, and I did like theory very much at that time, and I was a little bit torn between, you know, experiments or theory. But then, as it happened, for the equivalent of my year 4 project, which is in Italy, it's basically a work that you do in 1 year. So it's the first, the so-called tesi di laurea. So at the end of your degree, there is a really long dissertation. And for that dissertation, it just happened by randomly that my professor of particle physics at some point stopped me in the corridor and said, "Oh, would you like to do this project?" And I thought, and I said, yeah, okay, thank you, I'll think about it. And 10 minutes later, I knocked at his office and I thought, yeah, I'm going to do it. And so that was it. That was the start of my career in particle physics. And then I just stayed. So I don't know what would have happened if it didn't, you know, if he hadn't asked me on that particular day. So then I applied for a PhD, and yes, and then at that time I applied for 22 places of PhD, because after doing my degree, I was determined that I wanted to do a PhD in particle physics. So I did 22 applications. And I did my PhD in Italy, which involved an insane amount of paperwork to be sent around, at least at that time. And my mum was complaining terribly by the amount of money that I had to spend in postage. But nonetheless, I applied these 22 places, and then I got the first PhD place that I got, I just stopped there and got that one. So that's good. So I did my PhD, and then I decided to move abroad. So I did my PhD in Italy, and then I moved abroad. Indeed, I had my first postdoc in Edinburgh, where I met Vittoria, in the Na48 experiment, which studied this difference in behavior between matter and antimatter. And then and this was done with a particle called kaons, which contained the strange quark. And then I stayed in kaon physics, and these days I work in the Na62 experiment, a picture of which is just my background, my Zoom background. And so this experiment is looking still for very, very rare decays of the kaon particle. These decays are very well predicted theoretically, but very rare and very sensitive to new physics. And so we are trying to spot new physics beyond the standard model with this super precise decays of the kaons. So that's basically, so some years after Edinburgh, I moved to Cambridge and then to Birmingham, some years onwards. But yeah, but basically I've always worked in experiment at CERN.
Oh, sorry. Excellent. Thank you very much. I think we're going to move on to the Q&A questions. We've got 2 in the Q&A already, so we'll move on to that quite quickly, and then we'll go for the questions off the Google form. So we'll start with, and it's potentially quite a heavy one, is the Muon G2 experiment and the kind of results that they found. So someone wants to know essentially someone wants to know whether the deviation between what they found experimentally and standard model calculations are significant, and you know what they might mean for future particle physics.
So maybe I give my opinion and then Vittorio goes along. So yes, I mean, statistically it's significant if the theory uncertainties is what they are claimed. So considering the theory uncertainty claimed at the moment and the experimental uncertainty, it is a significant deviation. What indeed means, I don't think nobody knows at the moment. It could be various ways that new physics affect the G-2. And in several of these ways, we should be able to see other effects, both at LHC and in Keown physics as well. But the truth is, we don't know why precisely G-2 is deviating from the standard model.
Yeah, so if I look at the question, I mean, someone's explicitly said there's been some theoretical developments since the experimental announcement. So I saw that too. What I understand, so I'm no longer a theorist, but it's a very small effect. As a particle physicist, I would draw it as a Feynman diagram. I don't even know if it's the right one, but it's very complex to calculate, and there are many different ways, I don't know how many different ways of trying to calculate that same small correction. So it's part of G-2 that I think the new result is on. So there's lots of different pieces that go in that are calculated by different groups of people and then kind of put together. You can't always just add them up even. Sometimes you have to put them together more carefully than that. Yeah, so there was a calculation that changed the one result, which then made the discrepancy between the theoretical and experimental results smaller. But I think we have to wait. I think we have to wait for better experimental result with a smaller uncertainty. That's true, and that's coming. And also to see what other theoretical collaborations working on these small corrections come up with, because there's so many different ways to calculate it. I think we have to look at a lot of them. So the jury's still out. It is really exciting. I mean, I think that result, it's small, but it stinks of something interesting.
Yeah, and depending on the hypothesis of new physics, you should be able to see in Atlas, and depending on which case it is, I should be able to see in an A62, depending if it's an indication of new physics and what it is. So let's see.
Excellent. We'll carry on going. I think we'll stick with the questions I think that could be answered by the both of you for now. So I'll go for one from the Google form. So if you bear with me 2 seconds. So a lot when it comes to the kind of physics in general, a lot of it, I'm sure many physics students will agree with me that as you kind of go on with physics, is you kind of realize how much we don't know. And I think particle physics is something that's kind of very involved in that what we don't know sort of aspect. So where do you think particle physics is headed on that sort of trajectory with particles that that have been theorized but not discovered, or that kind of stuff? So that might not have been a very good wording of the question, sorry.
Well, I don't know. I really hope we are on the verge of some huge discoveries soon. We need to discover new physics because there is several shortcomings of the standard model. And so, I mean, yes, I really, really hope we are on the verge of changing our understanding of particle physics in a perhaps a dramatic way, a little bit like it happened, in the 60s where quarks were discovered, and then later on when CP violation was discovered, there was amazing, huge changes in the field. And hopefully we are on the verge of something similar soon, because we need to explain big things like the dark matter. CP violation is still not explained sufficiently. So there is a number of things that we really want to explain, and we don't know how they can be explained. I would say the thing is, we don't know what new physics is going to be, but for sure it will be exciting. wherever that is. The only thing is that we need to find it first. So it's slightly hard to predict exactly in which direction we are going to be. To me, it seems that progressively in these latest years, we've seen the infinitesimally small, like particle physics, come closer and closer to the very large scale of the cosmology and the universe. And I think that is a trend that is going to continue. But, and so because we hope with new physics to perhaps have a revolution again in particle physics, but also somehow to make a contribution to explain some of the big mystery of the universe. But apart from that, I think I cannot quite predict exactly in which way we are going to go. I think it's going to be big, but where, I don't know.
Yeah, I mean, it's actually, my opinion is completely, I was going to say inappropriate, but doesn't matter here at all, right? Nature has made her mind up, and it's for us to discover. So what I think doesn't matter, and I think that's the really exciting thing, but it's not quite as hopeless as that. So my postdoc supervisor had in his email sign-off, it said, chance prefers the prepared mind. So we can be prepared to help ourselves see whatever the new physics is, the new particles, the new forces, but we don't get to choose what it is. That's the chance. So it is still pretty exciting, and I don't know. I really don't know.
That was a really interesting way of looking at it, actually. So thanks. I'd not thought about it that way before. So we've got a couple of questions in the Q&A and in the chat box that are kind of related, and that's to do with the sort of the link between theory and experiment in particle physics. So potentially for you, Professor Martin, what it was like from going from a kind of theoretical undergraduate degree to a experimental postgrad qualifications, and then from the chat it was just kind of asking about what the links, or how much of a link is there between the theory and the experimental on the particle physics front.
Okay, so I should say I was never a fully fleshed theorist, and this is a poor choice, and I urge everyone not to make the same choice I did. But the reason I did mathematical physics, apart from physics, is I was not happy doing experiments in the lab. And I think Christina might even remember this. And it's not because I do not like experimental physics at all. I think actually, personally, I think it's more important than theoretical physics. But we certainly need both of them to take place. And so when I kind of switched from mathematical physics to experimental physics, I still, luckily for me, in particle physics, do not have to touch the equipment very much, because I have fabulous collaborators that are really good at that kind of thing. And I get to look at the data. I get to analyze the data that they take. I mean, that's the great thing about particle physics, is that it takes all sorts of people and we all work together in a collaboration to do it. I think someone was asking, did I have to catch up? Not really, because I mean, a lot of what I do is kind of statistical methods and kind of data analysis, and I hadn't done very much of that, I had to say, in my undergraduate degree, but it's something I could pick up because we had the training in it as well. So someone's saying, in a postgrad, would it be easy to switch? I think so. It's also, we don't do the one thing for the rest of our career, right? And I don't think anybody does. We're always evolving. We find new things interesting. We want new experiences. So actually, very occasionally, I do go into the lab. Someone tells me precisely exactly what to do, because, and I do it. And they'll always choose something quite simple for me, because I am quite clumsy. But And I really enjoy those days I do in the lab, but I'm never going to become a leader or an innovator in that. But you can pick up new skills as you go along, and people do. So I think it is possible to switch, maybe not from an electronics designer, which we do in our field, to someone that does mathematical calculations. I mean, those things are quite far apart, but there's a whole spectrum in between, and you can kind of go backwards and forwards along it.
If I may add one thing, I actually know somebody very successfully moved from almost phenomenology to firmware programming. So programming electronics board, because actually one thing is building the board himself and the other thing is programming them. So, you know, I mean, there is really a spectrum of activity that you can do. So, yeah.
Excellent. Thank you very much to both of you there. So I think we're going to move on to the next question that I'd quite like to ask. And it's sort of linked to the muon G-2 experiment, but generally particle physics experiments. They do take a very long time to sort of find results. A lot of the runs take, you know, years, and there are multiple runs. I think something linked to the University of Edinburgh is the discovery of the Higgs boson. That took quite a while from being theorized to being detected, and this, I think it's quite similar in the world of neutrinos as well. So with such long periods of time between, you know, the conception of an experiment and a discovery, how do you stay motivated between those 2 points? And you know, what's the sort of process behind conducting a particle physics experiment logistically?
Okay, I can start on this. Well, because I mean, you're right. If I explain to someone what I do in the general public, you know, I do explain, like, we found the Higgs boson, and then they will say, well, you know, didn't you do that 8 years ago? And I'm like, yes. Why are you still doing it? If you just look at the headline, it does look like that, but it's a process. I mean, and we work towards goals every month, every year, sometimes every week, sometimes every day. Sometimes I really have to do something that needs to be done for the next day. So I think, like any long-term project, it's always broken down. And if you're working as a PhD student, you will have a specific goal that helps the rest of the work, and so you will see what you are contributing to it. And we do need everybody to do their bit. That's why, I mean, when we found the Higgs boson, there was 4,000 odd names on the paper just from Atlas, and our colleagues on CMS had another 4,000 names. But we all did something that if it wasn't done, then we wouldn't have found the Higgs boson. I'm sorry, my kids in the background now getting a bit excited about something.
Yeah, so maybe I can just add on something about the perspective of a smaller experiment like NA48 and subsequently NA62. These are about maybe 250 people, let's say. It's much smaller experiments. Nevertheless, the time is also sizable from conception to the final result, because I mean, the experimental setup, it's complicated. I mean, it hasn't got this, if you want, the scale of Atlas where Victoria is, but nonetheless, both NA48 and NA62 are very long experiment, for example. And so there is a lot of subdetectors. So you do need to go from the conception to the construction of your detector. And most often, if you need to do cutting edge physics, you need cutting edge detectors. So you do need to develop a particular technique or some novel aspect of a detection technique, and that takes some time. So certainly some of the time is spent in designing and constructing and really physically building new detectors which have cutting edge performances, because for that particular measurement, you really need something new or something better. And then there is the aspect, if you want, the phase of accumulating the statistics for your measurement. And that also takes some time. Because despite having a very intense beam, you cannot do that in an extremely short time. You do need some time to accumulate the data. Now, the student in a smaller experiment like an A62 or the postdoc manage to do a range of activity. So they can either build or maintain and get going the detector, for example, as well as collecting the data and check the data quality, which is essential at the time, or, for example, work on the trigger, which is sort of the electronic brain that decides which event to take. And then there is the aspect of the data analysis, where once the data are collected, you need to extract the information from it. So it looks like a long time, but there are several jobs that comes with it. And both students and postdoc, at least in a small experiment, have the real chance to do almost all aspects. So it's a really a varied approach. So you don't get to do the same thing literally for 5 years. You got a range of things that you need to do, a very different range of things actually in this, in these years, and even in the year of 3 years of a PhD, for various part of it. And most often the students are responsible for an analysis, like Vittoria was, and in NA48, for example. And then they're responsible for the analysis, and they get to present the analysis to our colleagues. So in fact, the students are essential, and they are one of, people doing this and really, really at the forefront of it.
Excellent, thank you very much. Those were very insightful answers, I think. I've got a couple of follow-up questions. I think they're kind of linked to some of the subjects you touched upon. First of all, someone asks, what's it like as, what does your day-to-day schedule look like as a particle physicist? That's kind of linked to the breaking it down to smaller chunks, I suppose. I don't mind who takes it.
I can say, as a professor, I also do teaching and sit on committees, and supervise students. So unfortunately, I don't get to do enough of what I call physics. And anyone who's spoken to me this week on a Zoom call, the first thing I will have said, "Oh, I'm not doing any physics this week." But the physics that I'm doing at the moment for Atlas is I'm helping with validating the software we use in the trigger. And so the trigger is, I'll explain it specifically for Atlas because it's the best way I know how to. We have protons colliding. We have about, when we switch, so the LHC isn't on right now, but when we switch it on next year, there will be about 60 individual protons that hit 60 other individual protons every 25 nanoseconds. And that creates a hell of a lot of data. Most of it's actually really boring. It's just like proton and proton talk to each other, break each other apart, and spread into more quarks. And we don't care about that because we know that. So the trigger actually sifts through the data online as we take it and selects the most interesting collisions, and we keep those and then we analyze those later. So we're actually only trying to keep in about 100 collisions per second out of, I don't know what I was saying there, but millions. And so we need software to do this. Some of it's implemented in firmware, so actually in kind of programmable hardware. But I'm looking at the kind of simulation of this. So we run a huge simulation so we can tune exactly the algorithms to pick out the interesting events. And so my work at the moment is helping to validate this software. So I'm running a lot of jobs on the computer to generate these big samples, to look at these big samples. I actually don't do much of the analysis myself. I send it off to the experts to say, can you check that this is working for, if you want to look at Higgs bosons, is this keeping your Higgs bosons? Is this keeping your top quarks? Is this keeping the B physics events? So that's what my day-to-day work is. It's running jobs, it's checking the jobs ran, it's looking at the output of the jobs and then asking other people to tell me if that's what they need. So that's my day-to-day work at the moment at doing particle physics. But I still really enjoy it. I mean, it sounds a bit mundane, and perhaps it is, but I know that it's part of a bigger picture, and if that work doesn't get done, we won't take good data when we turn on next year.
So for me, I guess at the moment is a little bit special because at present I'm the spokesperson of the NA62 experiment indeed. So that is a little bit of a different angle somehow. Also, I mean, as being a professor, Vittorio is right. There is a number of teaching duty, a number of committee, and a number, students to supervise. But also, as a spokesperson, is also a bit about following how the experiment is doing, and because we are taking data this year, in fact, in 2 weeks' time. I know. It's about following exactly what's going on, try to see, and maybe something doesn't quite go as it should, so one needs to take decisions and maybe find plan A, B, C, D, and all of that in cascade, depending what happens. And it's also trying to find to place the right person in the right task to be able to work it out the most efficiently way. And also as a spokesperson, I have to sort of summarize and report to the funding agency and the committees, both at CERN and elsewhere, what the experiment is doing. So we are very pleased because recently we've been approved for taking data up to 2024 at least, so that's good. So somehow there is a little bit of admin that the spokesperson needs to do to get the things smoothly going forward. But also I enjoy very much to work with my PhD student to indeed look at data analysis, both for Pioneer New, which is our main physics goal, and also for example, lepton flavor violation searches and so on. So it's a varied job really, but as a spokesperson, I guess it's a little bit more heavy on committee reporting and logistics somehow.
Brilliant, thank you. That was very interesting to hear from both of you there. We've got a couple of questions that kind of follow a similar theme, in that the attendees would like to know what your opinions on having higher energy colliders. Are they worth the kind of cost that comes along with them? And if not, how else are we going to look at particles and discover new particles or new physics?
Okay, so the real answer is I don't know, because I don't know what physics has got in store for us. I mean, if of it, like to date, I would highly argue that everything we've built has been worth it, both in terms of just fundamental physics knowledge, but also the benefit to wider society in a lot of the spin-offs that you don't see but do come and impact everybody's life, all the taxpayers in Europe's life. And I'd like to think it's just the same if we build something at higher energy. But will we see, answer to the question? Who knows? Did you mention astroparticle physics as well? Because
yeah, that was kind of in the
how
else do we discover?
I mean, the universe luckily has its own acceleration mechanisms for particles, and certainly they can probably achieve higher energies than we can terrestrially. But what we can do terrestrially is the intensity. So we accelerate in the LHC 10 to the 11 protons at once. And at least 10 to the 11 protons at very high energies aren't impacting Earth for us to detect. So I think we need both. I think you need both of them. But the cost-benefit analysis, that's really hard to do. I'm sure people are looking at it, and I haven't read that specifically. But there will always be spin-offs from the work that we do. We'll always push things right to the edge, and they'll benefit not just us, other people too.
Yeah, I agree with Vittoria. I think that, well, one aspect, of course, is pursue the fundamental knowledge that in general it's worth doing in every side of fundamental science, not just particle physics. And so the particle physics as it is, the accelerators have the advantage of intensity, as Vittoria is saying, and also the fact that you can design the experiment to study something very specific. And so somehow, once you understand which avenue you want to pursue or which avenue it's more worth to pursue for the future, you can, in principle, tune your direction to a very specific investigation. So that is clearly an advantage. But I would also argue similarly that for society, there is a lot of spin-off that comes from the technology. And in many, many ways. So, I mean, in a sense, it starts always with fundamental science, fundamental physics, then it moves to, engineering, and then it cascades into society. It's just a process, but it starts from there.
Excellent. I think the rest of the questions are all sorts of general kind of advice questions based off your introductions. This is a question specifically for Professor Martin, but I think that both of you are qualified or more than qualified to answer it, because it's about looking at other kind of institutions other than the one that you kind of started at. So what are your views on that?
Well, there's always been a kind of rumor, and maybe there's an element of truth in it, that it's better to move around, and because if you can be successful in not just one university, one institution, I mean, it shows that you have flexibility and that you can cope with new situations. And especially if you go abroad, you'll find that the approach can be a bit different. In the way that we work, which is so it shows that you're flexible. I mean, however, there is more and more understanding that people don't just make decisions based on physics. They've got family lives. They want to be close to relatives, or these days people might just not want to have to travel as much. I mean, that anecdote I had at the beginning about flying over the Atlantic several times. This is not really good behavior anymore. Back then, we should have known better, but we didn't. So I think people do understand that people don't always want to move, and I think people are much more accepting if you've just stayed in one place for your whole career, as long as you can explain why you made those choices. I think that's fine. I don't think people should have to move if they don't want to. So certainly it's good for me. Back in the beginning of my story, when I said there was only 3 of us doing particle physics lectures with Professor Ken Peach, one other person in the class is now also a professor in Edinburgh. And so he did his PhD in Edinburgh. He went away for his postdoc, also America, not same place as me, and came back. And there's several of us in the department that have mainly been in Edinburgh. So it's certainly possible. And if that's what you want, I think that's what you should aim for. You shouldn't have to move just because other people tell you it's a good idea.
So I guess I moved a lot around. I even managed to travel quite a bit during COVID times. One of the very few person who managed to do that. Yeah. But apart from that, I would say that the important thing is to have a variety of experiences, which you can achieve that even if you not necessarily travel back and forth the ocean. I mean, I would not necessarily recommend to do exactly the same thing for many, many years, because I think to build a round-up professional, one needs to work on different experiments, or maybe even on different aspects of the same experiment. So that I would really strongly recommend, to try to have a round-up experience in terms of what you actually do, not necessarily move around as location. It may come to this or may not, but not necessarily is a must. My must is to try to have a varied experience regardless of the location.
Excellent. Well, I think we're going to start to wrap it up now, because the people for the next talk are here. I've just got a final kind of fun question for the both of you, and that is, do you have a favorite particle? And if you do, why?
Oh, we all have a favorite particle. So mine's supposed to be the Higgs boson, but it's not, because the Higgs boson only lives for 10 to the minus 22 seconds, and I really can't, give my heart to that. My favorite particle is the muon, because it's a lepton. It's fundamental. It's negatively charged. It lives a relatively long time, 10 to the minus 6 seconds, and it's also yellow.
So yes, I have a favorite particle. We all do, as Victoria says. Well, mine has to be the kaon. I think I've lived with strange particles all my career, and I'm going to say that they are definitely my favorite particles. So I like the idea of strangeness in all possible semantic and physics connotations. So I like the idea of something strange. So definitely I go for kaon.
That's definitely my favorite composite particle, Christina. So I'm definitely with you as well on that.
Nice. Brilliant. Thank you very much for your answers. They've been brilliant. I've really enjoyed kind of moderating the Q&A. So thank you very much for both of your time. Thank you very much to everyone in the audience who submitted their questions. We're very sorry we can get through all of them. I will, however, ask if the both of you, if you'd like to answer some more questions, you're very welcome to join our virtual conference space over at GatherTown. I can send you the link if you'd like. If not, no worries. Thank you very much again for joining us and giving your time very, very kindly. For the rest of you who are in the stream, we've got Dr. Abhijit Verma, who's going to talk about their work at the Extremely Large Telescope. So I hope you enjoy that. And I think over on stream B, we have a posters talk. So thank you very much for having us, and please enjoy the rest of the conference. Thank you very much.
Thank you for inviting us.
Thank you, Yed. Bye, everybody.
Bye.
Bye. Thank you.
Hi everyone. So we will start in about 5 minutes. So if you're still here from the previous talk, if you want to go and grab a quick drink or anything, now's the time. And in about 5 minutes time, we will come back. Hi everyone. So we'll just get started in a minute. So we'll just wait for it to turn 4 o'clock and then we'll get going. Okay, hi everyone. It's 4 o'clock now, so we will get going. If you've just joined us now, we will just go through a few things before we get started. So thank you very much for joining us. Throughout this talk, you will be muted and your camera will be off. So if you experience any technical difficulties, feel free to put them in the chat or the Q&A. Also, we will put a Google form for people to write any questions, so you can also use that as well. So, without further ado, okay, it's recording now. So I would like to introduce Dr. Aprajita Verma, who is from the University of Oxford, and their talk is Rise the Giant, the Extremely Large Telescope. So off you go. Thank you for being here.
Thanks very much, Nat. I'll try and share my screen. Hopefully that works.
Yep, you should be able to override ours.
So do you see the full screen view rather than the presenter view?
Yes, I believe I see full screen.
Okay, great. Thank you. Well, thanks very much for the invitation. It's a real pleasure to come and talk to you. So as Nat mentioned, I'm Aprajita Verma and I work in Oxford, and I'm going to tell you about a really exciting project that I work on, which is called, unimaginatively, the Extremely Large Telescope, because as you may have guessed, it is extremely large. And so I'm going to just kind of run through a bit of the background about why we're doing this, and hopefully give you a flavour of what this mega project is all about. So some of you may have seen this plot before. So this is kind of the whole universe encapsulated in one slide. Right back here, you have the Big Bang, leading to kind of the cosmic microwave background afterglow. There's a period of dark ages. And after that point, when the universe has expanded and cooled sufficiently, we get the first stars forming. And then as you go forward through to the present day, you see basically a change really in the kind of populations that are populating high redshift universe compared to those that we see in the present day. And so I did want to view who covered quite a lot of this already in their undergraduate courses. I'm going to speak a bit generally, so it may be below what you already know, but I'll do my best to keep it interesting. So one thing that I just wanted to mention and emphasize is that, you know, when we look at the electromagnetic spectrum, I think it's really important in terms of astronomy to realize that really our whole view of the universe has been completely dominated by this very narrow the EM spectrum that our eyes are sensitive to. In that, but before then, that was our. So I'm just going to show you kind of a compilation. Excuse me, I think I've managed to. Okay. I can't seem to advance myself. Okay, here we go. Hopefully you can see that. So this is just a galaxy called Centaurus A that we've kind of known for centuries. It looks like this in the optical. You see this kind of like hazy glow of stars, some kind of dust lane or some obscuration lying in front. But generally speaking, it's not the most thrilling galaxy to look at, although it's reasonably pretty. Then when you start looking at it in other wavelengths, this, for example, in the radio, you see these huge plumes of gas that are coming out. That's basically excited synchrotron emission. And that's clearly showing there's something a lot more exciting than what the optical image is showing us. Moving on to the X-ray, this is kind of reinforcing that radio view that there's something in the center of this galaxy that's producing these very collimated beams and jets. And that is also in the high energy as well as in the radio. And then it was only really in the last 20, 30 years that we've been able to do really detailed measurements in wavelengths that are different, so including the near infrared and the infrared. If you can see here, we talked about this kind of dust lane, but what you can see really is that we can't peer through that dust. And actually, you need the infrared sensitivity to be able to look through what is lying at the center of this galaxy. And if you look in the mid-infrared, so this was only enabled in the late 90s with the Infrared Space Observatory and the Spitzer Space Observatory, you can see there's actually a compact source right in the center that ties in extremely well with these jets and is the likely source of it. And that basically is what we think is a black hole that's basically creating this very energetic view of what we're seeing in the X-ray and the radio. So I'm just going to skip through to the compilation, but there you can see that if, our whole knowledge of the universe is really dominated by this optical view. And what we're really progressing into in the next decades is a real multi-messenger, a multi-wavelength view of the universe. And I think this object just nicely demonstrates that we really can't have a picture of the emission of objects in the sky unless we have all these complementary wavelengths to help us understand what's going on. So we're really in this state of big astronomy, and it's big in different ways. It can be big in terms of we're looking at large swathes of area, or it can be that we're looking at kind of objects in a lot of detail. And this is a nice picture of the Hubble Ultra Deep Field, where you can of really diverse and interesting objects. And we're really just scratching the surface of what these kinds of objects are. So just putting that into a bit more context in terms of what we do, just a really, it's actually a small fraction available in astronomy in terms of understanding the universe, but it's going right from radio, the SKA is a square kilometer array, down to the millimeter, through to the infrared, into the visible, and even up to what's going on. And it's really how we're going to understand or have a better complete picture. One of these, which is that's only true if you talk about optical and near-infrared astronomy, because the radio telescopes have had much bigger telescopes up to now. This is a 39-meter adaptive telescope. It works in the visible to the mid-infrared, and it's not, so it's being built by an organization, Southern Observatory. Basically, you need to have multinational collaborations to achieve projects of this scale. I know you were just speaking about particle physics, so in the same way that CERN requires many countries to fund it, that's also true for big astronomy now. And all these telescopes really can't be done by single nations on their own. And so there you see the flags of all the partners, and here you see kind of what this telescope is going to look like. So you might have noticed in the background there that it's not in an obvious place or a place that you recognize. And obviously we want to stay away from all these densely populated areas where there's lots of light pollution. So the ELT is actually going to be sited here in Chile. This is the Atacama Desert, where it's particularly high and dry. And so you can kind of see that the landscape is extremely barren. And one of the reasons it's very close to large telescopes that are also owned by ESO that exist here at Paranal. And this peak up here, Amazonas, is where the ELT is going to be built. And I think this this is a volcano about 200 kilometers away from the site, and you can still see it really clearly. For this is the other that is, as I mentioned, high and dry. That if you can see here, this is kind of the ocean, and this is the range. This is Paranal here, but you can see basically this is 25 kilometers from land. You've lots of bad weather coming over the mountain. You want Atacama Desert is exceptional astronomy. And so Chile have donated land to ESO to build the ELT as well as the Paranal site, and that's in return for 10% observing time on the observatory. So some of you, I guess this is quite some time ago, I think this was 2014, may have seen that there were some crazy astronomers blowing off the top of the mountain. And in fact, there was a live stream of the event. But as you can see there, it was a relatively quiet little blast rather than shaving off the top of the mountain. But they did do that, moved about 60 meters of height, leaving this huge platform here for the ELT to be built on. That's about 200 to 300 across. It's also on the ESO website, quite far, and there's, please go and have a look. You can catch that at this URL. This is actually state from early utility foundation dome. There's a nice flyby movie again that you can find on the ELT website, and you can see activity is currently paused because of the COVID pandemic, but they've really made exceptional progress. So I started working on this project back in 2009, and so it's really quite amazing to see this kind of level of work actually being made. It's been a long time coming, and we're so well. And so I'm just going to switch a little bit to talking about what kind of building these large facilities is like. So if you can imagine, going back to the 17th century when Galileo invented the first telescope, things have changed significantly. But even in that day, and even what we're doing now, the kind of advances in ground-based astronomy and even space-based astronomy goes hand in hand with technology, with engineering, with innovation, and computation. And that's really what enables us the science. Sometimes, and I'll come on to this in the next slide, sometimes it's the science that's driving those things, but often we're really either limited or we're pushing the boundaries of what can be achieved. And so to get from here over the last centuries to get to this is scope down here with its primary is really feat, and actually last century really of what we can achieve from telescopes. So fundamental telescope big science questions. It's still an open questions left in astrophysics and cosmology. We still need instruments and others to understand what's
we're currently experiencing some technical difficulties. I don't know if it's to do with connection. Hopefully it should sort itself out. Otherwise I'm just messaging some people. Are you still there, Dr. Burma?
Yeah, can you not hear me?
I can now. It went a bit weird, but I can hear you now.
Okay, I'm sorry about that.
No, don't worry. Don't apologize about it. It might be connection. It's quite weird. Can you still share your screen?
Is it not sharing?
Not right now. It just stopped.
Oh, right. Okay. Yep, sorry. Yeah, I was just carrying on talking, so I have no idea.
No, it went
what
odd.
people have heard. So do you see the big
Yes,
screen again?
I see it now.
And did you guys hear anything about this slide, or was I just talking to myself?
I don't know if Niccolo, I'm not too sure if I'm honest. We heard about this one, and I think that's when it started to go out around here.
With this one again.
Okay, sorry everyone, sorry for the delay.
That's okay, don't worry about it.
So basically there's nothing, I'm going to keep my camera off just because it will preserve bandwidth perhaps, but I am here and I'm speaking, hopefully you can hear me. So basically what the point I want to make is that you can't do big astronomy without big science, without big technology, and basically there's still a lot that we need to learn about the universe. Astronomy is definitely still in a stage of exploration and development. And I think it's also really important to understand that sometimes what we want to do to achieve the science is also driving innovation in technology. So for example, every Wi-Fi chip that is in every device that you use is basically a consequence of radio astronomy. And you can imagine what kind of impact that has. And that's, again, something that you can't really predict, but it's something that has revolutionized our lives. Also, I'm going to talk a little bit later about adaptive optics, which is correcting the blurring due to the atmosphere, and that's being used in medical imaging now. So there's lots of kind of things that come out of astronomy that you wouldn't necessarily expect, and certainly not things that we can always predict. So I think it's very true to say that new telescopes lead to very new and fundamental discoveries in terms of the science, but they also are innovative science, technology, computing and engineering programs. And hopefully these kind of big facilities like CERN and the ELT and various others are going to basically, hopefully, inspire you as well as train you when you become involved with them to be the next generation of pioneering scientists and engineers. So I've talked a lot about this telescope being big, and just to give you a sense of what that actually means. So you just saw Big Ben, for those of you familiar with the size of that. Now, this is a plot that basically shows the mirror size progression over the last century. And so we're starting here with the 2.5 meter telescope, which at its time was, really the biggest telescope around. And moving on to the present day, we have kind of the 5 meter Hale, which again was and it took. And then in the late 1990s to the 2000s, we had a whole host of 8 to 12 meter telescopes, which are these blue circles that you see here. I hope you can still hear me. So basically, this is where we are today. Here you have the 10 meter Keck. On the y-axis, you've got the altitude. We've got the tiny baby Hubble at the top there. And just to give you a sense of what the ELT is like, this red circle represents the diameter of the ELT, and it's larger than all the greater than 2 meter observatories put together. So the reason why kind of this is important, well, I'll get into that later, but it's also quite astonishing that every time we've had these kind of step changes, so going from the 2.5 to the 5 to the 10 meter telescopes, we've really made fundamental new discoveries about the universe, and the ELT will be no less. So for those of you who've been watching the Euro tournament, this is a size reference with respect to a football pitch. And there's the ELT primary overlaid. Randomly, I picked Stonehenge. So you can see it's a little bit smaller than the ELT primary. And bizarrely, the ELT primary is actually the same size in diameter as the world's largest pizza. So I thought that was quite amusing. So I learned this term from some amateur astronomers where I'd visited, called aperture fever, which basically encapsulates this slide that I showed you, that we're kind of forever going bigger and bigger and bigger. And why is that? And we kind of get wrapped up in in getting bigger, but what does it actually mean? But also I want to point out that achieving these kind of large apertures is really only possible, again, through innovative technology. So these are kind of mirrors from the Hale telescope, a 5-meter telescope that was in the 40s. And there you can see this really heavy, thick battle structure. This is the mirror itself, and it's extremely thick. Going to the present day, 1-meter telescope, and you can see this mirror is extremely different. This is extremely thin, it's very light, and it's very versatile. And the structure of the telescope itself is completely in contrast with the Palomar. This is battleship technology, whereas this light aluminium framework that basically bigger and bigger mirrors, as well as the mirror technology itself. We also need to do this in a very precise way. So one of the reasons why we've had much larger radio telescopes than we have had in the optical is because the precision you need to do precision astronomy is about 10% of the wavelength. So obviously in the optical with the surfaces, and again, it's the technology that's enabled us to really build these very precise 8.2 10-meter mirrors, where the precision of the mirror surface, as you can see here, is 0.00005 millimeters. And just to give you a flavor of what that means, that's like thinking about few centimeter ripples on the surface of something like the Atlantic Ocean. So you can kind of get a feeling for how incredibly precise the technology and the skills of those people who manufacture the mirrors are to enable that kind of precision surface. Bigger, your mirror sensitivity. It's a bit like when your pupils dilate in the dark to collect more light. And we also want, the spatial resolution you can resolve also increases as your diameter decreases. You can resolve finer and finer scales. So really what we're trying to get to is a deeper and finer view of the universe. And what do I mean by the LT site with a beautiful picture of the Milky Way over the top? So I'm just going to show you some slides about what I actually mean when I say we're going to get. So this is a cartoon that's been made up by Roberto Gilmozzi, which basically reflects what you can see in a normal night from the ground. This is what we call seeing limited mode. That's limited by the turbulence in the atmosphere. So in a given 1 arcsecond patch of the sky, this is what you would be able to see without a really brilliant telescope. This is what HST, which sits above the atmosphere, would see in that same region. So there you can start picking out, there's definitely a star here, there's a different colored star here, there's these what appear to be clouds here, some cloud there, and then a bright core in the center. When you start to look at that with the VLT, which is the 8-meter class telescopes, you can really start picking out much more in the background, as well as much more structure in all these things that you've seen already. And then finally, with the ELT, you can really see quite a lot of definition and detail. And so that's really what we're building the ELT for. But I mentioned it's the atmospheric turbulence that is not our friend. So this is just a movie of what basically the surface of the moon looks like when you're looking through the atmosphere. You see that the images are blurred. This crater that you see very clearly is actually, really not well defined. And the same thing happens to stars. So when you do a resolved movie of what a star looks like, it's not what we expect from, our typical images that we're familiar with from the HST. They're really kind of jumping around. And basically, when we sum that, we basically get this smeared out, what we call seeing limited image. So what we want to do is go from this kind of blurry, undefined star to actually what the optics of the telescope tell us, kind of define what a star, which is a point source, should look like. So you can see the atmosphere is really limiting what we can do. So over the last 20 years, there's been an incredible innovation called adaptive optics, and this movie just kind of shows it for the Gemini telescope. The ELT doesn't use the same system, but it's very similar. And this movie will just show you kind of what adaptive optics is. So essentially, you're basically looking at those movies of the stars where and you can't focus on basically collect light, and within your system, so the light gets kind of taken by the primary, reflected by the secondary into a unit, which has basically what we call a deformable mirror. So this is a very thin mirror that basically can be deformed. It has lots of actuators behind it that basically mimic the opposite of what the atmosphere is doing. So because you know what the optics of the telescope should provide you, so this is your distorted wavefront coming in, you have an active loop that basically then feeds the inverse of that back onto the surface of the mirror and produces these plane wavefronts. So you go from this kind of messy star to something that's basically what the optics of the telescope describe. So the reason, again, that we do this, so we're basically, this is what we see without adaptive optics. Basically, the image size of anything we look at in the universe is constant. All we do is that we gain in sensitivity because we're going to a bigger aperture mirror. So our benefit is basically goes with d squared. Once we add adaptive optics, our image size actually reduces also by a factor of d squared, along with the fact that we're also collecting more photons, means that we get a d to the 4 improvement in sensitivity and image quality. So something like the ELT will excel in collecting power and resolution. So it's basically about 5 times better angular resolution and 500 times faster exposures than an 8-meter telescope. And those of you familiar with Hubble Space Telescope images, it will be at 16 times better than what Hubble can deliver. So we're really able to get space quality images, but from the ground. And one problem with this is that this is, again, the Hubble Ultra Deep Field. And to do this correction, you need to look at a star. You need to look at a star to monitor what the atmosphere is doing to it. But in any typical deep field in the universe, there's basically no stars. And even the stars that are here, there's one there, and I think there's another one somewhere, but they're too faint to do this correction. So another step in innovation is to actually use laser guide stars. So this is basically using lasers to create an artificial star in the sodium layer of the atmosphere. And the ELT will have, this image shows 8 lasers, but it will actually have 6 that will create around the source that you want to look at, where you can monitor and make this adaptive optics correction. I'm just going to skip over these last slides, but this kind of actually, you know, we know that this works, and this is a test bench on the William Herschel telescope that happened a few years ago now. But this is basically a comparison of what you can see with HST, so there and there on this double binary source. And you can see, you know, this is only a 10-minute exposure or 20 minutes. And you can see you're already getting kind of Hubble space, better than Hubble telescope images already from the ground. And this is just on a 4-meter telescope. So you can imagine how well we can do with an ELT. Just to again give you some kind of reference to what I mean by deep and fine. So this is what basically a picture of the moon with the Moltke crater, which is about 6 kilometers across. So if we were to point the ELT at the moon, which we wouldn't do, but if we were, then basically this tiny dot here is about 300 times larger than the scale the ELT would be able to resolve. So it's a bit like you'd be able to see something like a double-decker bus. So it's about 10 meters on the surface of the moon. If the moon had an atmosphere, which obviously it doesn't, and I basically lit a candle, that change in flux from lighting the candle describes the sensitivity of the ELT. So a single candle flame at the distance of the moon would be picked up by the ELT. So again, gives you a flavor of the sensitivity. So I'm going to talk a little bit more about the telescope, and I'll try to go a bit more quickly. So again, it's it's a phenomenal instrument. You know, we're going from kind of telescope domes that you might have in your universities that are small and compact to things that are really more like football stadia. So the large, I've already shown you the primary on the football pitch, but if you imagine the next time you watch the actual dome of this telescope, basically is a similar size to a football pitch, and it's about 6.5 megatons. Yet it's still with incredible accuracy. It's all air conditioned and seismically isolated because there are active volcanoes in the region. I'm going to talk a little bit about the primary mirror. So we kind of discussed mirror technologies, but really the largest mirrors that we can actually make are about 8 meters across. So that's why we're kind of, you know, that's why we have this limitation at 8 meters. So in order to get over that, as you can see here, the actual primary mirror, which is 39 meters across, is actually made up of many individual hexagons. There's 798 in the primary mirror, and they're all about 1.4 meters across. Oh, sorry, I should switch off the funny sound here. But here you can see the primary mirror and its infrastructure and the structure that holds it down there while this movie kind of flies into the ELT. And basically every hexagon of mirror has 3 pistons behind it that basically distort the shape of that hexagon so that you basically preserve parabolic shape of the mirror. And you can imagine this whole telescope and this whole cradle is moving to track celestial objects. So it you know, even gravity as well as surface. And so again, an impressive bit of engineering that allows you to basically keep the mirror as precise as you can. These are people who are working on basically the pistons that do that distortion. And this is all being developed, and you know, the prototypes are already and working well. So the ELT actually has, and is going to be the only telescope in the world that has a 5-mirror design. So the light comes down from the universe, it hits the main primary, that gets reflected to a secondary mirror up here. And then there's a tertiary mirror down here that then sends it to the quaternary mirror. And then there's basically a flat fold mirror at M5, which sends the light out to these 2 platforms here, which is where the instruments will sit. So this is quite a complex, but it also goes fast. And just for those of you who are more familiar with telescopes, so the William Herschel telescope, which was the world's largest telescope for a long time, is basically the same size as secondary mirror. So it's like hanging the William Herschel telescope mirror above this giant primary. So this is what it all looks like. It's a telescope. And it also moves around in this way. And it's about itself, the structure itself, about 3,700 tons, yet it's motor driven to an accuracy of 0.3 arcsecond. And then just to give you a size reference, these Naismith platforms where the instruments will sit are about the size. And here down here, you can see the mini people, again, just to give you a flavor. I talked about this deformable mirror that does the adaptive optics, and the ELT actually has this built into the system. So M4 that does the deformation to adapt to the atmosphere. It's actually got 5 pistons behind it, or actuators, that are constantly making that deformation to the mirror surface to counteract what's happening in the atmosphere. These mirrors are all in production, and so things are progressing well. I'm not going to really go through this, but there's a suite of instruments, cameras and specs used on the ELT that will basically take the light that's measured and allow us to then interpret what we're seeing. And actually Oxford is involved in, and the UK are involved in all but one of those instruments, and Oxford is leading the first light imaging spectrograph, which is called Harmony. So there are other ELTs on the block. It's just a cartoon that kind of reiterates that the ELT is still the largest of the set. So there's 2 US projects, the Giant Magellan Telescope that uses basically 7 30-meter telescope. So again, you can see here that, we're really trying to make a whole suite of instruments that allow us to look at the universe in extremely high detail, and the ELT will be a forerunner. But I hope I've given you a flavour that, building telescopes is really a technological and an engineering issue that requires a lot of innovative thinking and physics and engineering to make it happen. And really the science is kind of almost the cream on the top. It's really what's driving decisions, but it's not all that we need to deliver the telescopes. So I'm going to talk kind of about the ELT science case. So basically, there are 3 foundations to the ELT science case. One is contemporary science. And what I mean by that is kind of the science that we already are doing with our telescopes, but they're limited because we simply don't have the sensitivity or the resolution. And this basically covers many of the cases we're all working on at the moment. So here's just some examples in the fields of planet and stars. If we're looking for signatures of Earth-like planets, so be looking at more giant and larger planets, including kind of trying to map their atmosphere and understand their spectral characteristics, and also understanding the circumstellar disks that they're being born in. In terms of stars and galaxies, there's a lot of open questions in the galaxies have ended up looking the way we do. We're able to look at basically resolved views of the galaxies. We're able to pick out individual stars in galaxies, not our own, but in the local group. There's still a lot of question, I showed you this funnel. Show you again shortly. There's been a transition in the way galaxies look like. And again, you need something that's very powerful and with high resolution to try and understand what might be influencing the nature of galaxies. And moving to the higher redshift universe and to cosmology, the ELT will also be able to help us detect galaxies at the very early universe, at the earliest of times. Some of you may have seen the news article that came out yesterday about some of the first stars. These are all things that the ELTs will help us also get information on. But we'd also be able to look at the physics of the galaxy. We can also make dynamical measurement of the expanded matter and dark energy and understand general relativity and other effects around black holes. So the second pillar or foundation is multi-wave energy. I've already spoken about that at the beginning, and essentially this ELT is part of something bigger. So there are synergies in kind of wavelength where we're matched in scale. There are also synergies in the sense that we're looking at the whole multi-wavelength spectrum, necessarily at the same scale, but with similar sensitivity. So there's lots of kind of parallels what we can achieve with all the future missions coming online. And the final foundation is the stuff that we don't know. So I talked about the contemporary science. Imagine, as I mentioned, with these kind of step changes in mirror size, you're actually really enhancing do to the degree that you can't even predict what we might see. And that's really where the experiment is going to come from. And that's where we really expect the spectacular new science to be born. So I'm going to go through a few of the cases. I won't have time to go through all of them. So I'm going to start with planets and stars. So this is what I mentioned before, this kind of funnel diagram. So we have kind of the present day. And so I'm going to focus on formation of planetary systems. So for those of you who are more familiar with it, you may recall that a lot of what we learned about exoplanets, which was a field when I was doing my PhD that just 20 years ago, we just seen the first exoplanets. So this is really a new and exciting field. But the planets that we mostly focus on are those that are kind of indirectly seen. Inferred presence is inferred by looking at the parent star of the systems. Basically, what we want to do is look at kind of the light from the stars themselves. So the ELT has the potential to directly image the planets themselves, learn more about the atmospheres through spectroscopy. And we currently know about, of order 4 to 5 exoplanetary systems, and many of them are beyond the scope of, really what their current scopes. Something that's really large with very good sensitivity to be able to discern the faint light of the planet from the very bright star that goes around it. The question we want to answer is, how do planetary systems, how common are systems like our own? What atmospheres do the planets have? Are there other Earths? And can we detect signs of life? These are all big questions that ELT will be able to achieve. There's been some really fantastic in complementary wavelengths in the millimeter with an array of millimeter telescopes. Look at this, to me, this looks like a simulation, but this is actual real data of basically dusty disks around stars, and the lines that you see are carving out their tracks within the orbits around these bright stars. And I just find this image phenomenal. And with the ELT, we'll be able to actually try and get systems, perhaps not exactly the same with slightly different properties, but we'll try and capture the light from these four planets. Like planets, so to look at planets in the habitable zone of stars, and most of the exoplanets that we can look at are kind of Jupiter or mega Jupiter exoplanet. What we really want to get to the rocky planets like Mercury, Venus, Earth, and Mars, which are faint.
Hi, we're currently experiencing some connection issues again. Hopefully, Dr. Verma should be back in a minute. So we'll just wait and see what happens. However, we will ask for the previous slide to be repeated.
Do you hear me, Nat?
Yes, hi, I do now. Yeah, you went out again on the last one.
I'm so sorry. I'm moving rooms to see if I can get a better signal.
That's okay, don't worry about it, it happens. Would you be able to repeat the last slide you were just on?
Yeah.
Okay, thank you.
Sorry, I'm having trouble finding the screen. Just a sec.
Whilst we're waiting, I'd like to thank everyone for who submitted their questions. We got quite a few questions already, and we will try to get through as many as possible once Dr. Verma has finished her talk.
Sorry about that. Do you see my full screen?
Yes, we do.
Okay. So I was just mentioning that, sorry, I don't know where I dropped out again, but just that we're trying to reach rocky planets, so kind of the Earth, Mars type planets, because a lot of exoplanet research is dominated by, kind of massive Jupiter-like objects, and rather we want to get to really reaching Earth-like planets and potentially those that lie in the habitable zones of their parent stars. I'm not going to talk about this, but there are various observational issues with detecting planets, and there are really innovative techniques in how to distinguish planets from optical features. That's what this movie shows, but it takes a bit of time. I also mentioned doing kind of spectroscopy of planets, and this is a little bit of a complicated diagram, but basically as planets orbit around their stars, you can actually take spectra, and when you see the kind of reflected light from the star, you basically see the combination of the stellar spectrum plus the atmosphere of the star, of the planet that's orbiting it. What you see on the right-hand side here is as this this planet is orbiting the star, the spectrum is changing, and the features that are changing allow you to basically disentangle the exoplanet spectrum from the stellar spectrum itself. So there's really quite a lot of innovation in terms of techniques to extract the information on extrasolar planets, and hopefully we'll be able to reach kind of spectral sensitivities so that we can actually see signatures of life in the spectra of exoplanets. I'm going to move now more to the galaxy side. So from the present day to kind of more established galaxies. And I think it's really fair to say, and this is just a snapshot of some galaxies, this is a slide from Joe Liske, but it really shows the galaxy menagerie. There's a huge variation in the types of galaxies we see, from things that look very ordered like the Milky Way to things that are far more kind of interacting or irregular or diffuse. And yet we still don't really have a clear picture of all these different mechanisms and why all these different types exist. So we want to know how and when did galaxies form? How did they build up their stars? What kind of environments did they get formed in? Why are there so many different types of galaxies, and what dominated that process? And also, how are the galaxies related to dark matter? So we have kind of a very good prescription of what dark matter is in the cosmological sense, and the simulations kind of agree reasonably well with our observations, but we still don't really have detailed physics on how the baryonic matter that makes up galaxies and the dark matter are related. So there's a bunch of things we can do, and I won't be able to have time to go through all of them, but something with the zoom power and the sensitivity of the ELT lets us really do things like galactic archaeology, which we can do in the Milky Way with our current telescopes, but now with the ELT, we'll be able to do that with galaxies within our local group. And that's basically looking at all the stellar populations within a galaxy and trying to figure out where those populations came from. So this is a simulation of the Milky Way and all the postulated merger events and accretion events that have created the stellar disk that we currently see. And we can do this now with the ELT for galaxies outside the Milky Way. We also know that there's been a dramatic change, and you can kind of see it back in this cartoon, that we have these kind of very well ordered large galaxies in the present day universe, but going back further, there's a lot more compact blue galaxies. And at some point, these kind of more red and dead galaxies that now dominate the local universe have been triggered. And we really don't know why there's this buildup of star formation, and then this kind of not very sharp, but definitely a turning point where most of the star formation in the universe ceased and the galaxies just then passively evolved. And that's a really big question. And one of those reasons may be the impact of black holes in the centers, which we think exist in the centers of most massive galaxies, that they have a much larger scale influence on what's happening within the galaxy itself, including expelling the gas from the galaxy and preventing further star formation. But we don't really have a good inventory of black holes. We can kind of, again, infer where they are and measure where they are, but we don't have very detailed observations. Now, what we can do currently, and this was part of the Nobel Prize for Physics that was awarded this year, was look at the black hole in our own galaxy. And here are some basically orbits of stars around that central dark mass that allowed them to constrain the mass and the other properties of the black hole. And this is really out of date now. Things have moved on quite significantly, but you can see you can track individual orbits of stars around our own central black hole. And this is a simulation from the 30-meter group on kind of, again, how well you can do compared to a 10-meter telescope with adaptive optics to what can be achieved with a 30-meter telescope. So you see you can track many more stars, and then equivalently, you can track stars around black holes, again, in galaxies in our own local group, really understand what the sphere of influence and the mass of the black holes in these systems are. Moving on to, sorry, Nat, I'm not quite sure how much time I have left.
Right,
but I'll try and put...
we have got some questions as well, which would be great to get onto, but if you've still got stuff to say,
I can wrap up now, and I'd rather get to the
okay,
questions.
if that's all right with you.
Yeah, sorry, I couldn't see the clock, so I'm sorry if I spoke too long.
No, that's fine, don't worry.
So there's lots of amazing things you can do. I won't get to the cosmology, but that's also possible with the ELT. So I was asked to kind of talk about my timeline, but I'm going to leave that to questions. And basically, I just wanted to bring out that the ELT is expected to have first light in 2027, so well within your future careers. If we were in Birmingham in person, you'd be able to have a size reference to the Birmingham clock tower there. This is the central area with the ELT primary mirror overlaid. And here are some links if any of you are interested in the ELT. I did want to highlight that the ELT presents lots of different opportunities, not just in the science, but in instrumentation, technology, computing and engineering, research and development, as well as project management. And while I take questions, I'll leave on this movie of us building the ELT out of Lego just for fun. So apologies again for all the connection issues and for running over time.
Oh, thank you so much for speaking to us. That was a really good talk and I found it really interesting. And I'm sure all the attendees did as well. So now we will get on to some questions. We've got quite a few, so I don't think we're going to get through them all. But the first question was, in your opinion, are more physics graduates nowadays pursuing applied physics rather than traditional / research-based physics, like particle physics and astrophysics, etc.?
No, I wouldn't say so. I don't have a good feeling for actual numbers, so I can't be very precise. But I think what's hard to convey is the physics that's in all the projects that are kind of behind the scenes, not the pure physics research projects. And I think if you're more kind of hands-on or enjoy experimental physics, there's a lot of opportunities for everyone, as well as having the more traditional ones. So, I think the opportunities are all there, and the numbers of PhD students are increasing. I think it's actually traditionally harder, at least in astronomy, to recruit instrumentation PhDs, and yet they're really driving a huge amount of innovation. I'm always in awe of the kind of actual physics they do compared to the physics in astrophysics, to be honest. A lot of what we do is more statistical and inferring things. So, it's hard to give that awareness, but I would say the chances for both are equally as good as they have been.
Okay, thank you for answering that one. The next one we have here, someone says, I currently work with a CHARA array looking at protoplanetary disks, where we use 6 1-meter telescopes rather than one large disk. If money wasn't a limitation, do you think a larger telescope is better than a telescope array with a large baseline length?
I think there's just a lot of challenges with optical interferometry. So there are, as well as the array that the questioner used, there's also the VLTs are also able to work together as an interferometer. And I think ideally it would be much simpler, I think, to have, many more small telescopes that we can do interferometry on. It's just really hard to get very good precision, and it's taken about 20 years for the VLTI instrument to deliver really good quality work. It's really challenging. So I think that's part of the limitation, is that people can do it and they are doing it, but it's really hard, and it's still hard to get a 39 meter, and it's hard to get the same quality and sensitivity. But I think they're all kind of complementary in that both the 1 meter interferometers and the 8 meter, they kind of conserve different areas of parameter space. So it's almost like you need everything, and not one is going to replace another.
Okay, so talking about then like more larger telescopes, on the topic of ridiculously large telescopes, do you think there'll be plans to resume discussions on constructing the overwhelmingly large telescope after the ELT has been done?
I think we're already there. Yeah, so it's great that your questioner brought up the overwhelmingly large telescope, because I like that because it's got a better acronym for a start. But also because it's just, again, this aperture fever. Like once you've got something, or even if it's not, we don't have any of these ELT yet, but we're already thinking about what we want to do bigger and better. And, there's lots of different concepts. I think the reason why the ELT was downgraded from the OWL telescope, which was 100 meters across, was because it wasn't seen as feasible. So you kind of have to mitigate cost and risk to be able to build something that you think is going to work. And that wasn't the case, 20 years ago, when they were deciding between 100 meter and a 40 meter. Now that, again, as I mentioned, the technology and the engineering will change, but I still think it's challenging. But we're already talking about it. So yeah, absolutely.
So as you just mentioned about VLT, when do you think VLT will become operational?
Well, they've had a few delays because of the pandemic, but they're hoping for 2027. And as you can see, there really are foundations now, and things are going ahead. The instrument teams have made great progress in. They're about to really start constructing the first instrument. So I really think within the next 5 to 6 years, we'll have the first images from the ELT.
Great, thank you. We'll have one final question because we're running out of time, but someone here has asked, are black holes considered baryonic or non-baryonic dark matter? I've read them described as both.
Yeah, I don't know the answer. And some of you may have seen recently there was a paper on the black hole the postulated black hole in the center of our galaxy is actually a fermion clump. I think we just don't know. We really don't know. And there's just so much like this that, we rely a lot on simulations and theory. And then when we kind of get near observational agreement, everyone's like, yay, we solved it. But have we? It's really almost like if you're an observational astronomer, you want to see the photons, or you want to see the proof. And sometimes it's just too hard. And I think things like VLTI, as well as developments at other wavelengths, may have a better way to answer that question than the ELT would.
Great, thank you for that answer. So we're getting to the end of time now, so we're going to wrap up. So thank you, Dr. Apachita Verma, for joining us and speaking to us. It's been great having you, and we're really honoured to have you here. And thank you for all the attendees for joining and all the questions you've gave. We've had absolutely loads of questions. I'm sorry we haven't been able to get through them all, but thank you. So at 5:30, we will be back on GatherTown doing just a chill social, some games in our virtual pub. So that'll be on there if you want to head over there. Dr. Verma, if you want to head over to GatherTown, either after this or even tomorrow, you're more than welcome to. if anyone else wants to ask you questions. Again, if you don't want to, that's absolutely fine, but you're more than welcome to. If you need links back, just let me know. So thank you for everyone for joining us. And if I don't see you guys in the pub, I hope you have a good evening.
Thank you. Yes, I think I'll be able to head over there for 10 minutes or so, but I'm also going to be on at 11 tomorrow in the Gather Town.
Okay.
If people have questions and they want to.
That's great. Thank you.